You are moving at 67,000 miles per hour right now, sideways, and you cannot stop. Not because your body is strapped to a planet, not because engines are firing somewhere out of view, but because 4.5 billion years ago, a cloud of gas and dust began to spin, and everything that came after, every rock, every moon, every living thing on Earth, inherited that motion. We call it an orbit. But what it really is a groove. A cosmic rut carved so deep into the fabric of space that nothing in this solar system has ever climbed out. Space feels like freedom, infinite blackness in every direction. No walls, no ceiling, no rules. And yet almost every probe, every satellite, every piece of metal we have ever flung into the void has gone the same way, sideways, along the ecliptic plane. The flat disk where the planets live, where the asteroids congregate, where gravity has gently, quietly insisted we stay for billions of years, there is a direction we almost never take, straight up or straight down. Not because it is forbidden, but because it is expensive, brutal, nearly impossible with the rockets we have built. In the entire history of space exploration, only one spacecraft has ever escaped the plane and flown over the sun's poles. One, out of thousands, and beyond that plane, in the vertical dark we have barely touched, there is a spherical prison 2 light-years wide, the Oort Cloud, a shell of trillions of frozen bodies drifting above and below us in total silence, and somewhere in that blind spot, things are moving. Rogue planets, interstellar objects, worlds with no star, falling through the ceiling at angles we were never designed to see. This is the story of the direction we cannot go, and what might already be coming from it. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You are moving at 67,000 miles per hour right now. Not in a car, not on a plane, just sitting there, reading this, breathing normally, entirely unaware that you are screaming through space at a speed that would carry you from New York to Los Angeles in less than 3 minutes. And you will never, not for 1 second of your entire life, feel it. That motion is not optional. You cannot step off. You cannot slow down. You cannot turn around. You are locked into a trajectory that has been running since before the first bacteria learned to split in two, and it will keep running long after every trace of human civilization has turned to dust. We call it an orbit, as if that makes it less insane. As if giving it a name explains why every single object in the solar system, from the smallest grain of sand to Jupiter itself, is caught in an endless sideways plunge with no finish line and no off-ramp. Space, we are told, is infinite. The universe stretches in every direction without limit. Up, down, forward, back, total freedom. You could point a spacecraft in any direction you want and just go. That is the fantasy. That is what the word space conjures in the human imagination. Boundless possibility. The reality is more like being on a train, a very fast train that never stops, never slows, and whose tracks were laid down 4.5 billion years ago. You can move around inside the train. You can walk toward the front or the back. You can technically jump off if you are willing to spend an obscene amount of energy doing it, but no matter what you do, the train itself is still moving, and it is moving sideways, always sideways. The feeling of being stationary is a lie your senses tell you, because everything around you is lying in exactly the same way. Your house is moving at 67,000 miles per hour. The tree outside your window is moving at 67,000 miles per hour. The air in your lungs, the ground beneath your feet, the continent you are standing on, all of it hurtling through the void in near-perfect unison. There is no jolt, there is no wind in your hair. Your body is not equipped to detect constant motion. It only notices changes, acceleration, deceleration, a sudden stop. As long as everything around you is moving at the same speed in the same direction, your nervous system treats it as stillness. Richard Feynman, the physicist who had a gift for explaining uncomfortable truths in plain language, put it simply: you only feel changes in motion, not motion itself. Your body is a change detector, not a speed detector. Which means the 67,000 miles per hour you are traveling right now might as well not exist as far as your biology is concerned, but it does exist, and it matters, because that motion defines what you can reach, where you can go, and what parts of the universe are fundamentally off limits, unless you are willing to pay an energy cost so high that most destinations simply are not worth it. To understand what is actually happening, you need to zoom out. Picture the sun, not as a glowing ball sitting peacefully in the center of a diagram, but as an object falling. It is falling around the center of the Milky Way galaxy, which sits roughly 26,000 light-years away from where we are right now. The sun completes one full lap around the galactic core every 230 million years or so. That orbit is not slow. The sun is moving at about 514,000 miles per hour relative to the center of the galaxy. That is fast enough to cross the entire United States in about 20 seconds, and it is dragging the entire solar system with it. Earth, Mars, Jupiter, the asteroid belt, every comet in the Oort Cloud, all of it caught in the sun's wake, following the same curved path through space like beads on a wire. Now zoom in closer. Earth is not sitting still relative to the sun either. It is falling around the sun in its own smaller loop, completing one orbit every 365.25 days. That orbit is what gives us years. It is also what gives us our 67,000 miles per hour. Technically, the number is closer to 66,600, but we are rounding because at this scale, a few hundred miles per hour is a rounding error. The point is, Earth is not traveling with the sun. It is traveling around the sun, while the sun travels around the galaxy. The shape that traces through space is not a circle. It is not even an ellipse, though that is what we call Earth's orbit when we draw it on a flat piece of paper. In 3 dimensions, taking the sun's motion into account, Earth's path looks more like a stretched spring, a helix, a corkscrew spiraling forward through the galaxy, endlessly looping around a moving center that is itself looping around an even larger center, sideways and forward at the same time, never up, never down, always circling. And here is the thing that makes this more than just a fun fact to impress people at parties. That motion is not just describing where Earth happens to be at any given moment. It is defining the default trajectory of everything humans have ever built that leaves the surface. Every rocket we have ever launched inherits Earth's 67,000 miles per hour the instant it clears the atmosphere. You do not start from zero when you go to space. You start from 67,000, and depending on where you want to go, that inherited speed is either your greatest asset or your greatest obstacle. Want to go to Mars? You are already moving in roughly the same direction Mars is moving, which helps. Want to leave the solar system entirely? That 67,000 miles per hour is now pointed in the wrong direction. You are moving sideways relative to the exit, which means you need to spend fuel, a lot of fuel, to change your velocity enough to escape. Want to go straight up, perpendicular to the plane of the solar system? Now you are fighting the full force of your orbital speed, all 67,000 miles per hour of it, because up, in that sense, means leaving the train, and leaving the train means cancelling out all the motion the train gave you for free. The engineers who design space missions do not think about the solar system as a map. They think about it as a web of overlapping velocities. Every object in the solar system has a speed and a direction. To get from one object to another, you do not just point your spacecraft at the target and go. You change your velocity until your orbit intersects the target's orbit at the right moment. You are not flying to Mars. You are adjusting your fall around the Sun until your fall matches Mars' fall at the same place and time. Orbits are not places. They are speeds. Destinations are intersections, and everything always is moving sideways. For most of human history, none of this was obvious. Early astronomers looking up at the night sky saw lights that moved across a fixed dome. The stars rotated overhead in perfect circles. The sun rose and set. The moon waxed and waned. Everything appeared to revolve around Earth. And why would you think otherwise? The ground beneath your feet felt solid, stable, motionless. The sky moved. You did not. The ancient Greeks built elaborate models to explain what they saw. Crystalline spheres nested inside one another, each carrying a planet or a star, rotating at different speeds to account for the changing positions of celestial objects. The system worked. It predicted eclipses. It tracked the planets well enough to be useful for navigation and timekeeping. It just was not true. The first crack in the model came from the planets themselves. The word planet comes from the Greek word for wanderer, and the planets earned that name by doing something the stars did not. They moved against the background of the fixed stars. Most of the time, they drifted steadily eastward. But every so often, a planet would slow down, stop, reverse direction for a few weeks, then stop again and resume its normal path. Astronomers called this retrograde motion, and it was a nightmare to explain if you assumed Earth was the center of everything. The Greek astronomer Ptolemy patched the problem by adding epicycles, small circles layered on top of the larger circle of each planet's orbit. A planet did not just move around Earth. It moved in a little loop while it moved around Earth, and that combination of motions created the illusion of backward movement. The math worked, predictions improved, but the model was getting complicated, suspiciously complicated. When Nicolaus Copernicus published his heliocentric model in 1543, placing the Sun at the center instead of Earth, retrograde motion became simple. The planets were not actually moving backward. Earth was just passing them in its own orbit, and from our moving perspective, they appeared to reverse direction the same way a car on the highway seems to drift backward when you pass it. No epicycles, no nested spheres, just different orbits around a common center. Copernicus did not have all the details right. He still thought orbits were perfect circles, which they are not. But the shift from geocentrism to heliocentrism was the beginning of understanding that we are not standing still, we are moving, and everything we see in the sky is a product of that motion. Johannes Kepler refined the picture in the early 1600s with 3 laws of planetary motion that are still taught in every introductory astronomy class. The first law said orbits are ellipses, not circles. The second law said planets move faster when they are closer to the Sun and slower when they are farther away, sweeping out equal areas in equal times. The third law connected a planet's orbital period to its distance from the Sun. Kepler did not know why any of this was true. He just knew it fit the data better than anything else. Isaac Newton supplied the why a few decades later: gravity, a force pulling every object toward every other object with a strength that depends on mass and distance. The planets do not move because crystalline spheres are pushing them. They move because they are falling toward the Sun, but they are also moving sideways fast enough that they keep missing. That is what an orbit is, a controlled fall, a balance between the pull of gravity trying to drag you inward and your sideways velocity trying to carry you past. Get the balance exactly right, and you fall forever in a closed loop, never hitting the ground, never escaping. Newton also gave us the principle of inertia, which he borrowed and refined from Galileo. An object in motion stays in motion unless a force acts on it. That is why you do not feel Earth's orbital speed. Nothing is pushing you, nothing is pulling you sideways. You are just continuing to move in the same direction at the same speed you have always been moving, because that is what objects do when left alone. The idea that motion is relative, that there is no universal reference frame, became even clearer with Albert Einstein. Special relativity, published in 1905, formalized what Newton had hinted at. Speed is not a property you have. It is a relationship between you and something else. You can measure how fast you are moving relative to the sun, or relative to the galactic center, or relative to the cosmic microwave background radiation left over from the Big Bang. But none of those measurements is more correct than the others. There is no cosmic speedometer mounted somewhere in space showing your true speed. There is no privileged center of motion, which brings us back to the 67,000 miles per hour. That number describes Earth's speed relative to the Sun. If you measure Earth's speed relative to the galactic center, you get a different number. The Sun is moving at about 514,000 miles per hour around the galaxy, and Earth is moving around the Sun, so depending on where Earth is in its orbit, its speed relative to the galactic center could be 514,000 plus 67,000, or 514,000 minus 67,000, or somewhere in between. Different frame of reference, different speed, same motion. Zoom out further, and the numbers get even stranger. The Milky Way itself is moving, relative to the cosmic microwave background, which is the closest thing we have to a universal reference frame. Our galaxy is traveling at about 1.3 million miles per hour. That motion is the combined result of the initial expansion of the universe, the gravitational pull of nearby galaxy clusters, and the large-scale structure of the cosmos itself. We are falling toward the Virgo cluster. The Virgo cluster is falling toward the Great Attractor. The Great Attractor is part of an even larger structure called the Laniakea supercluster, and that entire web of galaxies is being pulled in directions we are still mapping. Every layer of motion stacks on top of the one below it. Earth around the Sun around the galaxy through the local group through the universe. At no point in that entire nested hierarchy of movement is anything sitting still, and yet if you close your eyes right now and try to feel it, you feel nothing, because your body, your chair, the floor, the building, the continent, the planet, all of it is moving together. We live on a train, inside a train, inside a train, and every single one of those trains is moving sideways. The word orbit comes from the Latin orbita, meaning track or course. The Romans used it to describe the wheel rut left by a cart, a groove worn into the road by repeated passage. That is what an orbit is, a groove. Not a physical one carved into space, but a path defined by velocity and gravity that every object follows unless something pushes it out. Earth has been following the same groove for 4.5 billion years. The groove is so old that continents have formed and broken apart. Oceans have filled and drained. Entire branches of life have evolved and gone extinct, and the orbit has not changed by any amount a human would notice. It will still be there long after we are gone. The groove is older than bones. It is older than photosynthesis. It is older than the moon. That groove, that relentless sideways motion, is not just a feature of where we happen to be. It is the reason we are here at all. Without it, Earth would have fallen into the Sun billions of years ago, and every spacecraft we have ever launched, every satellite, every probe, every crewed mission, all of them are riding inside that same groove unless we spend enormous amounts of energy to climb out, which raises the next question. If everything in the solar system is locked into this sideways drift, moving in nearly the same flat plane, endlessly circling, is there a ceiling? Is there a floor? What happens when you try to go up? The groove is older than you can imagine, and I do not mean that in the metaphorical sense where people say something is really old, and what they actually mean is a few hundred years. I mean the groove, the flat orbital plane in which Earth and nearly everything else in the solar system travels, has been running for 4.5 billion years. It was cut into the fabric of space before there was an Earth to orbit inside it, before there was a moon, before there were continents or oceans or a single amino acid floating in a warm tide pool. The groove is the ecliptic plane, and it is the most fundamental piece of architecture in the solar system. If you want to understand why we are trapped moving sideways, why every planet orbits in nearly the same direction along nearly the same flat band, why launching a spacecraft straight up is so punishingly expensive, you have to understand how this groove formed in the first place, and why, after 4.5 billion years, it has refused to go away. The story begins with a cloud, not a small one. A cloud of gas and dust roughly 15 billion kilometers across, drifting through interstellar space about 4.6 billion years ago. Most of it was hydrogen and helium, the leftover material from the Big Bang. Mixed in were heavier elements, carbon, oxygen, iron, silicon, forged inside previous generations of stars that had lived, died, and scattered their guts across the galaxy. The cloud was cold, just a few degrees above absolute zero. It was also completely unremarkable. Clouds like this drift between the stars all the time. Most of them stay clouds. This one did not. Something disturbed it. Possibly a nearby supernova sent a shockwave rippling through the region. Possibly the gravitational tug of a passing star nudged it just enough to tip the balance. Whatever the trigger, a small region near the center of the cloud began to collapse. Gravity pulled inward. Gas compressed. As it compressed, it heated up, and as it heated up, something else happened that would define the shape of everything that came after. The cloud started to spin. This is where angular momentum enters the picture, and angular momentum is the reason the solar system is flat. Angular momentum is a property of rotating objects. It depends on how much mass is moving, how fast it is moving, and how far that mass is from the center of rotation. The critical feature of angular momentum is that it is conserved. Once a system has it, it cannot get rid of it unless something external comes along and takes it away. The collapsing cloud had angular momentum because no cloud in the universe is perfectly still. Even a tiny amount of rotation, a drift so slow you would never notice it, becomes significant when the cloud starts to shrink. As the material fell inward, the rotation sped up. This is the same reason an ice skater spins faster when they pull their arms in. The mass is moving closer to the center, so to conserve angular momentum, the rotation rate increases. The cloud spun faster. Faster spin meant more centrifugal force pushing outward, and that outward push worked against gravity. In the directions parallel to the spin axis, there was no centrifugal force. Material could fall freely inward along the poles. But in the plane perpendicular to the spin axis, the rotation created an outward pressure that slowed the collapse. The result was a shape that every astronomer who studies star formation has seen 1,000 times. The cloud flattened into a disk. Picture a ball of pizza dough spinning in the air. Gravity wants to pull it into a sphere. The spin wants to fling it outward. The compromise is a flat disk, thicker in the middle, thinner at the edges. The protoplanetary disk that became our solar system followed the same physics. At the center, where most of the mass concentrated, the young sun began to ignite. Hydrogen atoms slammed together under immense pressure and heat, fusing into helium and releasing enough energy to light up the surrounding region. Around that newborn star, a disk of leftover gas and dust spread outward for billions of kilometers. The disk was not uniform. Temperatures near the sun were scorching, hot enough to vaporize rock. Farther out, past what would become the asteroid belt, temperatures dropped low enough for water to freeze. Even farther out, methane and ammonia condensed into ice. The temperature gradient split the disk into zones, and those zones determined what kinds of planets could form where. In the hot inner region, only materials with high melting points survived: metals, silicates, rocky minerals. These materials stuck together through a process called accretion. Dust grains collided and stuck, pebbles formed. Pebbles collided and stuck, boulders formed. The process fed on itself. Larger objects had stronger gravity, which let them pull in more material, which made them larger still. Over millions of years, the inner disk gave birth to the rocky planets: Mercury, Venus, Earth, Mars, small, dense, made of metal and stone. In the outer disk, beyond the frost line, the story was different. Water ice was abundant, and ice made up a much larger fraction of the available solid material than rock alone. Objects grew faster out there because there was simply more stuff to work with. Some of those objects grew large enough, fast enough, that their gravity started pulling in not just solids but gas. Hydrogen and helium from the surrounding disk poured onto these growing cores. They became the gas giants: Jupiter, Saturn. Farther out still, where the disk was thinner and colder, the ice giants formed. Uranus, Neptune, smaller than Jupiter and Saturn, but still massive enough to hold thick atmospheres of hydrogen, helium, and methane. The key point, the detail that explains why all of this ended up moving in the same flat plane, is that the material never stopped being a disk. The gas and dust that made the planets was already rotating in a thin sheet. When particles collided, they tended to average out their vertical motion. A grain moving slightly upward would hit a grain moving slightly downward. The collision would cancel out the up and down components, leaving only the sideways motion. Over time, countless trillions of collisions smoothed the disk into an even thinner, flatter structure. By the time planets finished forming, they had inherited the motion of the disk they were born from. That motion was overwhelmingly in one direction, along one plane. The ecliptic plane is not a law of nature, it is a fossil, a relic of the solar system's birth, frozen into the orbits of every large object that survived. The word ecliptic comes from the Greek eklypsis, meaning abandonment or vanishing, the root of the word eclipse. Ancient astronomers noticed that eclipses only happen when the sun and moon align along a specific band in the sky. That band is the ecliptic, the path the sun appears to trace across the sky over the course of a year. From Earth's perspective, the sun moves eastward through the zodiac constellations, passing through Aries, Taurus, Gemini, and so on, returning to its starting point after one full orbit. That apparent path is actually a projection of Earth's orbital plane onto the sky. The ecliptic plane is the flat sheet in space that contains Earth's orbit. By extension, it serves as the reference plane for the entire solar system. When astronomers describe the tilt or inclination of another planet's orbit, they measure it relative to the ecliptic. Earth's equator is tilted 23.4 degrees relative to the ecliptic. That tilt is why we have seasons. When the northern hemisphere is tilted toward the sun, It receives more direct sunlight and experiences summer. 6 months later, when the northern hemisphere is tilted away, it is winter. The tilt is not optional. It is baked into Earth's rotation, the result of collisions and gravitational interactions during the chaotic final stages of planet formation. The ecliptic itself has its own tilt. Relative to the plane of the Milky Way galaxy, the ecliptic is tilted by about 60 degrees. That number tells you something important. The solar system is not aligned with the galaxy. The disk of planets around the Sun is sitting at a steep angle compared to the disk of stars around the galactic center. There is no reason it had to be that way. The orientation of the protoplanetary disk depended on the random spin of the gas cloud it collapsed from. A cloud in a different part of the galaxy might have collapsed into a disk aligned with the galactic plane. Ours did not. We are tilted off-axis askew. The ecliptic is thin. If you measured the solar system from top to bottom, the distance from the plane where most of the planets orbit to the farthest vertical extremes is tiny compared to the system's width. The major planets, Mercury through Neptune, all have orbital inclinations of less than 7 degrees relative to the ecliptic. Mercury has the largest inclination at about 7 degrees. Venus is tilted just 3.4 degrees. Earth defines the plane, so its inclination is 0 by definition. Mars is 1.8 degrees, Jupiter 1.3, Saturn 2.5, Uranus 0.8, Neptune 1.8. If you drew the solar system to scale, the planets would look like they are glued to a sheet of glass. The thinness is not an accident. It is a consequence of the disk's formation. Objects that strayed too far from the plane either collided with something and had their orbits flattened, or they were ejected entirely during the early chaotic period when Jupiter and Saturn were still migrating. That thinness has consequences for everything we do in space. When NASA launches a probe to another planet, the mission planners do not have to worry much about vertical alignment. Mars and Earth are both moving along nearly the same flat plane. The problem is timing and speed, not altitude. You launch when the two planets are in the right positions relative to each other, and you adjust your velocity to match Mars's orbit when you arrive. If Mars orbited at a steep angle to the ecliptic, getting there would require a massive velocity change perpendicular to Earth's motion. You would have to cancel out a huge chunk of your sideways speed and redirect it upward or downward. The fuel cost would make the mission vastly more expensive, possibly prohibitively so. The fact that Mars, like Earth, is locked into the same groove is the only reason we have been able to send dozens of spacecraft there without bankrupting the space program. Changing orbital inclination is expensive. In orbital mechanics, the term is delta V, short for change in velocity. Every maneuver a spacecraft makes costs delta V, and delta V translates directly into fuel. The more you need to change your velocity, the more fuel you need to carry. Fuel has mass, and mass makes the rocket heavier, which means you need even more fuel to lift the extra fuel. The tyranny of the rocket equation, as it is sometimes called, makes certain maneuvers borderline impossible with current technology. Launching straight up out of the ecliptic plane is one of them. Earth is moving sideways at 67,000 miles per hour. If you want to leave the plane and head perpendicular to it, you need to cancel out all 67,000 miles per hour of sideways motion and redirect it into a new direction. That costs an enormous amount of delta V. You cannot just point your rocket up and go. You are still carrying all that sideways speed with you. To truly go straight up, you have to stop moving sideways first. And stopping is just as hard as starting. Most spacecraft do not even try. Instead, they use gravity assists and carefully timed burns to gradually tilt their orbits over multiple flybys of planets. Even then, getting significantly above or below the ecliptic takes years and an enormous amount of planning. The plane is not a physical barrier, there is no wall, but energetically it might as well be one. The groove is easy to stay in and hideously expensive to leave. Which brings us to the question of why nothing has left. If the ecliptic is just the leftover shape of a disk that formed 4.5 billion years ago, why has it not dispersed by now? Why are the planets still following the same flat paths they started on? The answer is that orbits in the ecliptic plane are stable. Stable does not mean static. It means the system has reached a configuration where small disturbances do not grow into large disruptions. The planets tug on each other gravitationally, and those tugs cause small shifts in their orbits over time. Orbital periods lengthen and shorten, eccentricities increase and decrease, inclinations wobble slightly. These changes are called secular variations, and they happen on timescales of tens of thousands to millions of years, but the variations are bounded. The planets do not spiral into the sun, they do not fly off into interstellar space, and they do not suddenly start orbiting at wild angles to the ecliptic. The plane is dynamically self-reinforcing. If a small object, say an asteroid, were somehow knocked into a highly inclined orbit, it would start crossing the paths of planets that are moving in the ecliptic plane. Sooner or later, it would have a close encounter with one of them. That encounter would either eject it from the solar system entirely or, more likely, gravitationally scatter it back into a lower inclination orbit. The plane acts like a gravitational attractor. Objects that deviate too far either leave the system or get pulled back in. There are exceptions, of course. Pluto is the most famous one. Pluto orbits the Sun with an inclination of about 17 degrees, far higher than any of the major planets. That steep tilt is part of why Pluto was reclassified as a dwarf planet in 2006. It does not dominate its orbital neighborhood the way the 8 major planets do, and its orbit is chaotic on long timescales. Pluto is also locked in a resonance with Neptune, orbiting the Sun exactly 3 times for every 2 Neptune orbits. That resonance stabilizes Pluto's orbit and prevents it from colliding with Neptune, even though their paths cross when viewed from above. Pluto is not alone. The Kuiper Belt, the region of icy bodies beyond Neptune, contains thousands of objects with inclined orbits. Many of them were scattered into their current trajectories by gravitational interactions with the giant planets during the early solar system. They are the survivors, the objects that got kicked around but did not get kicked out. Comets are even more extreme. Some comets travel on orbits inclined at 60, 70, even 90 degrees to the ecliptic. A few orbit the Sun in the opposite direction from the planets, moving retrograde. These objects come from the Oort Cloud, a vast spherical shell of icy debris surrounding the solar system at distances up to a light year from the Sun. The Oort Cloud is not a disk, it is a sphere. Objects in the Oort Cloud have orbits oriented in every direction because they were scattered there by gravitational encounters with Jupiter and Saturn billions of years ago. Once an object is that far from the Sun, the tiny gravitational tugs from passing stars and the galactic tide can shift its orbit. Over millions of years, the orbit can be tilted, stretched, or redirected entirely. When one of these distant objects gets nudged inward, it falls toward the Sun on whatever trajectory it happens to have. If that trajectory carries it through the inner solar system, we see it as a comet. Because Oort Cloud objects have no preferred orbital plane, comets can appear from any direction. They are the exceptions that prove the rule. Everything that formed in the protoplanetary disk stayed in the disk. Everything else was thrown out. The ecliptic is not just a product of the solar system's history, it is a constraint on its future. As long as the Sun exists, As long as the planets continue orbiting, the plane will persist. There is no mechanism to erase it, no friction to slow the planets down, no external force to tilt them into new orientations. The groove has been running for 4.5 billion years, and it will keep running for billions more. When the Sun finally exhausts its hydrogen fuel and begins to die, swelling into a red giant and incinerating the inner planets, the survivors will still be moving along the ecliptic. Even after the Sun sheds its outer layers and collapses into a white dwarf, any remaining planets will keep orbiting in the same flat plane they have always followed. The groove outlasts everything. It outlasted the formation of Earth. It will outlast the end of Earth. It is the most durable structure in the solar system, not because it is made of anything, but because it is made of motion. And motion, once established, does not stop unless something stops it. For every human mission that has ever left Earth, the ecliptic has been both a gift and a prison. It is a gift because most of the destinations we care about, the Moon, Mars, the asteroids, Jupiter, Saturn, all of them live inside the same groove. You do not have to fight your way out of the plane to reach them. You just have to time your launch, adjust your speed, and let gravity do the rest. It is a prison because the moment you want to go anywhere else, anywhere not aligned with that ancient disk, the cost becomes staggering. The energy required to leave the plane scales with how much speed you need to change, and at 67,000 miles per hour, even small angular changes add up fast. Going perpendicular to the ecliptic, straight up into the solar system's attic, or straight down into its basement, is theoretically possible. Humans have done it exactly once, and the spacecraft that did it was not designed to come back. It was designed to look, to see what the solar system looks like from outside the groove, to measure what happens when you finally, after 4.5 billion years, break the plane. Nobody had ever seen the Sun's poles. That was the problem. For decades, spacecraft had visited every major planet in the solar system. We had flown past Jupiter's moons, skimmed Saturn's rings, photographed Uranus and Neptune from close range. We had sent probes to Venus, Mars, and Mercury. We had built an entire catalogue of planetary surfaces, atmospheres, and magnetic fields. But the Sun, the object at the center of it all, the star that defines the solar system and powers every living thing on Earth, remained half invisible. Because every spacecraft we had ever launched to study the Sun was trapped in the same flat plane as Earth, the ecliptic plane, the groove, and from inside that groove you cannot see the poles. You are stuck looking at the equator. From Earth's perspective, the Sun appears as a disk, a flat circle. We see one hemisphere at a time, the side that happens to be facing us. The top and bottom of the Sun, the polar regions, are tilted away from our line of sight. They remain hidden, not because of any physical barrier, but because of geometry. We are sitting inside a disk, looking at the center of that disk. It is like trying to see the top of someone's head while standing directly in front of them. You cannot do it unless you move. And moving, in this context, means climbing out of the ecliptic, going vertical, leaving the groove. That costs energy, an enormous amount of energy, more than any chemical rocket could deliver on its own without a clever trick. So for the first 30 years of the space age, solar physicists studied the Sun from the equator and tried to infer what the poles might be doing based on models, magnetic field measurements, and a lot of educated guesswork. The guessing was not satisfying. The Sun is a ball of plasma, a churning mass of electrically charged particles threaded through with magnetic fields that twist, stretch, snap, and reconnect in ways that still defy complete understanding. The Sun's magnetic field drives everything that happens on its surface and in its atmosphere. Sunspots, solar flares, coronal mass ejections. The solar wind, a constant stream of charged particles flowing outward from the Sun at speeds exceeding 1,000,000 miles per hour. All of it is controlled by magnetism, and magnetism on the Sun is not uniform. The equator and the poles behave differently. At the equator, the Sun rotates once every 25 days. At the poles, rotation slows to about 34 days. That difference in rotation rate, called differential rotation, twists the magnetic field into complex shapes. Field lines that start out running smoothly from pole to pole get stretched and tangled as the equator outruns the poles. Over time, the field becomes a mess. The mess builds up energy. Eventually, the field snaps, releasing that energy in the form of solar flares and coronal mass ejections. This process is called the solar dynamo, and it operates on an 11-year cycle. At solar minimum, the Sun is relatively quiet. The magnetic field is simple, mostly dipolar, like a bar magnet. At solar maximum, the field is chaotic. Sunspots multiply, flares erupt constantly. The poles during this time may even reverse polarity. North becomes south, south becomes north. The flip happens every 11 years. We know this because we have been tracking sunspots and magnetic activity for more than a century. What we did not know before Ulysses was what the field looked like at the poles during different phases of the cycle. Did the polar regions participate in the dynamo process, or were they isolated? Was the solar wind coming from the poles different in speed, density, or composition than the wind coming from the equator? Were there structures in the polar corona that we simply could not see from the ecliptic? Those questions mattered not just for solar physics, but for understanding space weather. The solar wind does not stay at the Sun. It expands outward, filling the entire solar system with a bubble of charged particles called the heliosphere. When that wind slams into Earth's magnetic field, it can disrupt satellites, damage power grids, interfere with GPS, and create the auroras. Predicting space weather requires understanding where the wind comes from and how it behaves under different solar conditions. And you cannot build a complete model of the solar wind if you have only ever measured half of it. The idea for a polar solar mission dated back to the early 1970s. Scientists knew what they needed to do. They just did not know how to do it cheaply enough to get approval. The problem was delta V. To reach an orbit that passes over the Sun's poles, you need to tilt your trajectory out of the ecliptic by about 90 degrees. That is not a small adjustment. Earth is already moving at 67,000 miles per hour along the ecliptic. If you want to move perpendicular to that, you need to cancel out a huge chunk of your sideways speed and redirect it into a new direction. The math is brutal. A direct launch from Earth to a polar solar orbit would require more fuel than any rocket in existence could carry. You would need a booster the size of a skyscraper just to lift the fuel tanks, and even then, the numbers did not close. Engineers looked at the problem for years and kept arriving at the same conclusion. It could not be done. Not with chemical rockets, not without a trick. The trick was Jupiter. Jupiter is the largest planet in the solar system, 318 times more massive than Earth. Its gravity is strong enough to deflect spacecraft at high speed without slowing them down. If you approach Jupiter at the right angle and the right speed, you can use its gravity to change your direction. Not by burning fuel, by stealing energy from the planet's orbital motion. The planet does not notice. Jupiter is so massive that the energy it loses is negligible. But for a small spacecraft, the change in trajectory can be enormous. This technique is called a gravity assist, and by the 1980s it was well understood. Voyager 1 and Voyager 2 had used gravity assists at Jupiter and Saturn to reach the outer planets and eventually leave the solar system entirely. The same technique could work for a polar solar mission. Launch a spacecraft toward Jupiter. Time the arrival so the spacecraft swings around Jupiter's poles. The gravity assist bends the trajectory, flinging the spacecraft out of the ecliptic and into a highly inclined orbit around the Sun. No massive fuel tanks required, just careful planning and a long wait. NASA and the European Space Agency ESA decided to build the mission together. They called it Ulysses, named after the Greek hero who wandered for years trying to reach home. The name was fitting. The spacecraft would spend more than a decade looping through the solar system, visiting regions no probe had ever seen. Ulysses was not designed to be fast, it was designed to be patient. The spacecraft itself was relatively simple. A boxy structure about 3 meters tall, covered in thermal blankets and bristling with antennas and instrument booms. No cameras. This was not a mission that would return stunning images of distant worlds. Ulysses carried instruments to measure particles, magnetic fields and radiation, plasma detectors, magnetometers, cosmic ray sensors, a solar wind analyzer, a radio science experiment. Its job was not to look at the sun, its job was to taste the environment around the sun from angles that had never been sampled before. Total mass at launch was about 370 kilograms, small by interplanetary standards. The spacecraft was built to survive. It carried a radioisotope thermoelectric generator, an RTG, the same kind of power source used by the Voyager probes and later by Cassini and New Horizons. An RTG uses the heat from decaying plutonium to generate electricity. No solar panels. Solar panels would have been useless. Ulysses was going to spend years far from the sun, and even when it passed close to the sun during its polar loops, the spacecraft would be oriented in ways that made solar power impractical. The RTG provided steady power for the entire mission, 19 years as it turned out, far longer than anyone expected. Ulysses launched on October 6, 1990, aboard the Space Shuttle Discovery shuttle mission STS-41. The payload bay carried the spacecraft along with a 2-stage solid rocket booster called an Inertial Upper Stage IUS. After Discovery reached low Earth orbit, the crew deployed Ulysses and the IUS from the payload bay. The IUS fired, sending Ulysses on a trajectory toward Jupiter. From that point forward, the spacecraft was on its own. The journey to Jupiter took 16 months. Ulysses traveled outward across the solar system, passing Mars's orbit, crossing the asteroid belt, moving farther from the Sun than any spacecraft designed to study the Sun had ever gone. The mission team spent that time checking instruments, calibrating sensors, and watching telemetry to make sure the spacecraft was healthy. On February 8, 1992, Ulysses reached Jupiter. Closest approach came within about 450,000 kilometers of the planet's cloud tops. Not a particularly close pass by the standards of missions like Galileo or Juno, but close enough. Jupiter's gravity grabbed hold of the spacecraft and bent its trajectory. Ulysses came in from below Jupiter's equator, swung around the planet's south pole, and shot back out at a steep angle to the ecliptic. The gravity assist worked exactly as planned. The spacecraft's velocity relative to the Sun barely changed. What changed was the direction. Ulysses had been moving mostly sideways along the ecliptic. Now it was moving upward, climbing out of the plane at an angle that would carry it over the Sun's south pole, across the Sun's equator, over the North Pole, and back down again. The orbit was not circular. It was a long ellipse tilted 80 degrees to the ecliptic. Orbital period, just over 6 years. That meant Ulysses would make one full loop, from South Pole to North Pole and back, every 6 years. And because the solar cycle runs on an 11-year rhythm, the spacecraft would get a chance to observe the poles during different phases of solar activity. One pass during solar minimum when the sun was quiet. One pass during solar maximum when the sun was going berserk. The first polar pass came in 1994. Ulysses crossed the sun's south pole in September of that year. The spacecraft was about 300 million kilometers from the sun, roughly twice Earth's distance. From that vantage point, instruments sampled the solar wind streaming out from the southern polar regions. What they found surprised almost everyone. The solar wind at the poles was fast, much faster than the wind at the equator. At the equator, the solar wind moves at about 400 kilometers per second. At the poles, during solar minimum, the wind was screaming outward at more than 750 kilometers per second. That difference matters because it tells you something about the structure of the sun's magnetic field and corona. The fast wind comes from coronal holes, regions where the magnetic field opens up and allows material to escape freely into space. The slow wind comes from closed magnetic field regions where material is trapped and heated, then released in bursts. At solar minimum, the sun's magnetic field is mostly dipolar. The field lines at the poles are open, pointing straight out into space. That creates a clear, unobstructed path for the solar wind to accelerate. At the equator, the field is more tangled. Field lines loop back on themselves, slowing the wind down. Ulysses was measuring this difference directly for the first time, not inferring it from models, not guessing, directly sampling the wind from above and below. The spacecraft continued north. In 1995, it crossed the sun's equator and began climbing toward the North Pole. In July of that year, it passed over the North Polar regions, completing the first ever survey of the sun from pole to pole. The data confirmed what the southern pass had shown: fast wind at the poles, slow wind at the equator. Clean magnetic field structure at high latitudes, complex, twisted fields near the equator. The picture that emerged was one of a sun divided into zones, not just in terms of rotation rate, but in terms of magnetic behavior and wind speed. For solar physicists, this was a breakthrough. It meant that models of the solar wind and the heliosphere could no longer treat the sun as a uniform source. The poles and the equator were fundamentally different environments, and those differences had consequences for everything downstream, including Earth. Space weather models had to be updated. Heliosphere models had to be revised. The sun, it turned out, was more complicated than anyone had given it credit for, and Ulysses had only just started. The spacecraft completed its first orbit and came back for a second polar pass in 2001. By then, the sun was near solar maximum. The difference was dramatic. At solar maximum, the sun's magnetic field is a chaotic mess. The poles no longer have clean, open field lines. Coronal holes shrink or disappear. The fast solar wind slows down. The boundary between fast and slow wind blurs. Ulysses measured all of this in real time, watching as the sun's polar regions transformed from quiet, fast wind zones into turbulent, variable regions that looked more like the equator. The magnetic field at the poles reversed polarity between the first and second passes, just as sunspot observations had predicted. But Ulysses was there to measure the reversal directly. The data showed that the reversal was not a sudden flip. It was a gradual process that took months, with the field weakening, breaking apart and reforming in the opposite direction. That level of detail, observing the sun's magnetic poles through an entire activity cycle, had never been possible before. Ulysses made it routine. The mission kept going. A third orbit, a fourth. Every 6 years, the spacecraft returned to the poles, each time sampling the solar wind under different conditions. In 2004, during the third polar pass, Ulysses discovered that the solar wind was weakening. The pressure of the wind, the rate at which it carried mass and energy away from the Sun, had dropped by about 25% compared to measurements from the mid-1990s. Nobody knew why. The Sun's total energy output had not changed. Sunspot activity was following its normal cycle. But something about the solar wind's structure had shifted. The discovery raised new questions about long-term variability in the Sun's behavior and whether the solar wind's strength fluctuates on timescales longer than the 11-year solar cycle. Ulysses also measured cosmic rays, high-energy particles streaming into the solar system from outside, remnants of supernova explosions and other violent events across the galaxy. The solar wind pushes against these particles, creating a boundary called the heliosphere that partially shields the inner solar system. When the solar wind is strong, fewer cosmic rays make it through. When the wind weakens, more cosmic rays penetrate. Ulysses tracked this variation over nearly 2 decades, providing a long baseline of data that astronomers are still analyzing. By 2008, the spacecraft was running out of power. The RTG's plutonium was decaying, as it had been since launch, and the electrical output was dropping. The mission team started shutting down instruments one by one to conserve power for the most critical systems. The spacecraft's hydrazine fuel for attitude control was also running low. Ulysses relied on spinning to maintain stability, and small thruster burns were needed occasionally to correct its orientation. Without fuel, the spacecraft would eventually lose the ability to point its antenna toward Earth. In June of 2009, after more than 18 years in space, Ulysses sent its final transmission. The mission officially ended. The spacecraft is still out there, orbiting the Sun in its tilted pole-to-pole trajectory. It will keep orbiting for millions of years, long after the instruments have gone silent and the structure has been sandblasted by micrometeoroids. A permanent monument to the one time humans managed to break the plane. The mission proved something that everyone suspected but no one had demonstrated. Leaving the ecliptic is possible. You do not need exotic propulsion or science fiction technology. You need patience, precision, and a very large planet. But the cost, even with a gravity assist, is high. Ulysses took 16 months just to reach Jupiter. It spent another 3 years climbing to its first polar pass. From launch to first science data over the poles, the mission took 4 years. And that was with everything going perfectly, no second chances, no course corrections that could not be planned years in advance. One shot, one trajectory, one spacecraft carrying a handful of instruments because that was all the mass budget allowed. The mission returned about 4 gigabytes of data. That is less than a single high-definition movie. By modern standards, it is almost nothing. But those 4 gigabytes contained the first and only direct measurements of the solar wind at high latitudes over a full solar cycle. The data is irreplaceable. No other mission has done what Ulysses did, and as of now, no other mission is planned. There have been proposals, concepts for new polar solar probes with better instruments, higher data rates, closer passes to the Sun. None of them have been funded. Not because the science is not valuable, it is, but because the cost and complexity of leaving the ecliptic makes every such mission a hard sell compared to missions that stay in the plane. The groove is easy, vertical is hard. Ulysses also underscored something uncomfortable. Even with a gravity assist, even with Jupiter doing most of the work, the mission barely managed to climb out of the ecliptic. The spacecraft's orbit was tilted at 80 degrees, not 90, 80. It did not pass directly over the Sun's poles. It passed to the side at a distance of about 2 astronomical units. far enough that the sun looked like a bright star, not a nearby furnace. To get closer, to actually fly over the poles and through the sun's corona, the way the Parker Solar Probe now dives toward the sun's equator, you would need even more delta V, even more fuel, or an even more elaborate series of gravity assists that would take decades to execute. The groove is not just a feature of the solar system's architecture, it is a constraint on what we can reach and how fast we can get there. Breaking the plane once, briefly, with a single spacecraft, took the combined resources of 2 space agencies, a shuttle launch, a Jupiter flyby, and nearly 20 years of operations. Breaking it routinely, sending missions above and below the ecliptic as easily as we now send probes to Mars, is beyond our current capability, not because the physics does not allow it, because the energy cost is too high and the payoff, in terms of accessible destinations, is too uncertain. There is one more place where breaking the plane matters, one region of the solar system where the ecliptic does not apply, where objects move in every direction without preference, where the groove finally ends. It is not a place you can visit, it is not even a place you can see. It is a shell of frozen debris so far from the sun that sunlight takes more than a year to reach it, and everything inside that shell is waiting. Waiting for a nudge, waiting to fall, waiting to come screaming down through the plane toward the sun, carrying with it a reminder that the solar system is not as flat as it looks, that beyond the groove there is a ceiling, and sometimes things fall through it. There is a place where the groove ends, a place so far from the sun that calling it part of the solar system feels like a technicality. A shell of frozen debris hanging in the dark, 2 light-years wide, wrapped around everything you have ever thought of as the sun's domain. Most people have never heard of it. The ones who have usually picture it wrong. They imagine a belt, a disk, another flat plane like the ecliptic stacked on top of the others. They are wrong. The Oort Cloud is a sphere, a perfect bubble of ice and rock surrounding the solar system on all sides, above, below, and every direction in between. It is the only major structure in the solar system that does not care about the ecliptic. It does not orbit in the groove. It orbits around the groove, enclosing it like a shell around an egg. And if you want to understand the true shape of the sun's gravitational prison, the real boundaries of the cage we are all locked inside, you have to understand the Oort Cloud, because it is not just the edge of the solar system. It is the ceiling, the floor, the walls. It is the sphere we cannot leave without stealing velocity from something else. And everything inside it, every comet, every frozen rock drifting in the outer dark, is waiting for a reason to fall. The Oort Cloud is named after Jan Oort, a Dutch astronomer who did not discover it, did not observe it, and never saw a single object confirmed to be inside it during his lifetime. What Oort did in 1950 was solve a problem that had been bothering astronomers for decades. Comets kept showing up from random directions, not just random in the sense of unpredictable timing, though that was true too, random in the sense of orbital geometry. Some comets arrived from above the ecliptic, some from below. Some came in at steep angles that had nothing to do with the flat plane where the planets lived. These were long-period comets, objects with orbital periods measured in thousands or even millions of years. They would appear once, swing around the sun, and vanish back into the dark. If you mapped their orbits backward, tracing the path they had taken to reach the inner solar system, the lines did not converge on any single region. They came from everywhere. That was the problem. Short-period comets, the ones that return every few decades or centuries, were easier to explain. They came from the Kuiper belt, a disc-shaped region of icy debris beyond Neptune. The Kuiper belt sits in the ecliptic plane, so comets coming from there naturally arrive along predictable paths. But long-period comets did not behave that way. They did not respect the plane. They arrived from above, below, from angles that made no sense if they had originated in a disk. Oort proposed a solution. What if there was a second reservoir of comets, much farther out than the Kuiper belt? Shaped not like a disk, but like a sphere, a cloud of icy bodies surrounding the entire solar system at enormous distances, so far from the Sun that their orbits were barely bound by gravity. Objects in such a cloud would have no preferred orbital plane. They would move in every direction, their paths determined not by the ancient spin of the protoplanetary disk, but by random gravitational nudges from passing stars and the tidal pull of the Milky Way itself. When one of those objects got nudged inward, it would fall toward the Sun on whatever trajectory it happened to have. Sometimes that trajectory would carry it through the inner solar system at a steep angle to the ecliptic. We would see it as a long-period comet arriving from an unexpected direction. The hypothesis explained the data perfectly. It also meant the solar system was vastly larger than anyone had realized. The Kuiper belt extends to about 50 astronomical units from the Sun, 50 times the distance from the Earth to the Sun. That felt big. The Oort Cloud, according to Oort's calculations, started somewhere around 2,000 astronomical units and extended outward to maybe 100,000 astronomical units. At that distance, the Sun is not a disk. It is a bright star. 1 light-year is about 63,000 astronomical units. The Oort Cloud, if Oort was right, reached halfway to the nearest star. Nobody has ever seen the Oort Cloud, not with a telescope, not with a spacecraft, not directly. Every object we think belongs to the Oort Cloud has been identified by working backward from comets that arrived in the inner solar system. You watch a comet, measure its orbit, calculate where it came from, and if the numbers say it originated more than a few thousand astronomical units away, you call it an Oort Cloud object. That is the only evidence we have, comets that came from the right distance. For decades, that was enough. The hypothesis worked. It explained long-period comets. It explained why they came from random directions. It explained why their orbits were so elongated, stretching from the outer reaches of the solar system all the way in to the Sun and back out again. But as observational technology improved, astronomers started to realize the Oort Cloud was not just a hypothesis. It was a requirement. Without it, the solar system did not make sense. The current model divides the Oort Cloud into 2 regions. The inner Oort Cloud, sometimes called the Hills Cloud, after the astronomer Jack Hills, who studied it in the 1980s, is shaped more like a thick torus, a donut. It starts at a few thousand astronomical units and extends to about 20,000. Objects in the inner cloud still retain some memory of the ecliptic plane. Their orbits are inclined, but not randomly. There is still a bias toward the plane, a leftover signature of where they came from. The outer Oort cloud is the sphere. It starts around 20,000 astronomical units and extends outward to somewhere between 50,000 and 100,000, possibly farther. The exact boundary is fuzzy because at those distances, the Sun's gravity is so weak that even tiny perturbations from passing stars can strip objects away. The outer Oort cloud is less a fixed structure and more a probabilistic zone where objects might be bound to the Sun or might not be, depending on what else happens to be wandering through the neighborhood. Estimates for the total number of objects in the Oort cloud range from a few trillion to several trillion. Most of them are small, a kilometer or 2 across. Some are larger. A few might be hundreds of kilometers in diameter, large enough to qualify as dwarf planets if they were anywhere near the inner solar system where we could see them. The total mass of the Oort cloud is uncertain. Some estimates put it at a few times the mass of Earth. Others suggest it could be significantly more. Nobody knows. You cannot count objects you cannot see. The question of where the Oort cloud came from is messier than you would expect for something this fundamental. The obvious answer is that it formed along with the rest of the solar system, condensing out of the same protoplanetary disk that gave us the planets. The obvious answer is wrong. The Oort cloud did not form where it is now. It formed much closer to the Sun, in the region where the giant planets were assembling. Picture the early solar system 4.5 billion years ago. The Sun has just ignited. The protoplanetary disk is still thick with gas and dust. Rocky planets are forming in the inner region. Farther out, beyond the frost line, icy planetesimals are colliding and sticking together, building the cores of what will eventually become Jupiter, Saturn, Uranus, and Neptune. Not every planetesimal gets incorporated into a planet. Most of them stay small. And as the giant planets grow, their gravity starts flinging those leftover planetesimals around like a child scattering marbles. Jupiter, being the largest and closest to the Sun, was the most efficient at this. Any icy body that wandered too close to Jupiter got accelerated. Some were thrown inward toward the Sun, where they either collided with something or got ejected from the solar system entirely. Others were thrown outward, sent flying into the outer reaches of the solar system at high speed. Most of those ejected objects left the solar system completely. Their velocity was high enough to escape the Sun's gravity. But some of them, a small fraction, were launched at speeds just below the escape velocity. They climbed outward, slowing as they went, until they reached a point where the Sun's gravity was barely strong enough to hold them. There they stopped climbing and began a slow fall back inward. Except they never made it back, because by the time they reached the outer limits of their orbits, millions of years had passed. The solar system had moved. The Sun and all the planets had traveled partway around the Milky Way. And in that time, other stars had drifted past the solar system, close enough that their gravity gave the distant planetesimals a tiny nudge. Not enough to send them flying into interstellar space. Just enough to change their orbits slightly, shift the angle, randomize the inclination. Over billions of years, those nudges added up. The planetesimals that had been thrown outward in roughly the same plane as the ecliptic were scattered into every possible orientation. The sphere formed not because the objects were placed in a sphere, but because their orbits were randomized by external forces over geological timescales. The Oort cloud is not a structure, it is a graveyard, a collection of debris that got kicked out of the planetary formation zone and never came back. The difference between the Oort cloud and the Kuiper belt comes down to distance and time. The Kuiper belt is close enough to the Sun, and its objects are moving fast enough that passing stars and the galactic tide have not had time to fully randomize their orbits. The Kuiper belt is still a disk because it is still young, dynamically speaking. The Oort cloud is a sphere because it is old. It has had 4.5 billion years to forget where it came from. Objects in the Kuiper belt orbit the Sun every few hundred years. Objects in the outer Oort cloud take millions of years to complete a single orbit. At those distances, at those timescales, the Sun is barely in control. A star passing within a light year of the solar system, an event that happens every few million years, exerts enough gravitational pull to alter the orbits of Oort cloud objects significantly. The Milky Way itself exerts a tidal force on the Oort cloud. The galaxy is not a uniform gravitational field. One side of the Oort cloud is slightly closer to the galactic center than the other, and that difference in gravitational pull stretches the cloud tugging on objects and slowly changing their trajectories. Over millions of years, the galactic tide is enough to dislodge objects from the outer Oort cloud and send them either inward toward the Sun or outward into interstellar space. This is how long-period comets are born. An object sits in the Oort cloud for billions of years, drifting in the dark, frozen solid, inert. Then something happens. A star passes nearby. The galactic tide shifts. A giant molecular cloud, one of the massive structures where new stars are forming, drifts through the region, and its gravity pulls on everything within a few light years. The Oort cloud object's orbit changes. The change is tiny at first, a slight decrease in orbital energy, a small inward nudge, but over millions of years that nudge compounds. The object's orbit shrinks. It begins falling toward the Sun. The fall takes thousands of years, tens of thousands. The object crosses the outer solar system, passes Neptune, crosses Uranus, crosses Saturn, crosses Jupiter. As it gets closer to the Sun, it starts to warm up. Ice begins to sublimate. Gas and dust stream off the surface, forming a coma and a tail. By the time it reaches the inner solar system, it is glowing, visible from Earth, moving fast. We call it a comet. It swings around the Sun, possibly breaking apart from the heat and gravitational stress, and then it begins the long climb back outward. Most long-period comets never return. Their orbits are so elongated that even small gravitational nudges from the planets during their close approach can change the trajectory enough to eject them from the solar system entirely. They came from the Oort cloud. They will not be going back. Some long-period comets do return. If the orbit happens to bring them close to Jupiter during their inward fall, Jupiter's gravity can capture them, pulling their orbit into a shorter, more circular path. These comets get converted into short-period comets. They stop being Oort cloud objects and start being inner solar system objects. Over time, repeated passes near the Sun boil away their ice. They become inactive. Dead comets, rocky bodies that look like asteroids but started their lives as icy debris from the outer reaches of the solar system. Some of the asteroids in the asteroid belt may have started as comets. We cannot tell by looking anymore. The ice is gone. What remains is indistinguishable from any other rock. The Oort cloud is not static. It is leaking. Objects are being pulled out by passing stars, by the galactic tide, by random gravitational encounters. At the same time, new objects are not being added. The era of planet formation ended billions of years ago. Jupiter is not throwing planetesimals into the Oort cloud anymore. The cloud is slowly evaporating. In another few billion years, it will be significantly smaller. In 10 billion years, when the Sun swells into a red giant and begins to die, the Oort cloud will still be there, but it will be a shadow of what it is now. Most of its objects will have been stripped away by the chaos of the galaxy. The sphere versus plane dichotomy is more than a geometric curiosity. It is a statement about control. The ecliptic plane exists because the Sun's gravity is strong enough, and the objects within it are close enough that they remember where they came from. The plane is a fossil of the protoplanetary disk, preserved by the sheer dominance of the Sun's gravitational field over everything within a few tens of astronomical units. The Oort cloud exists because the Sun's gravity, at distances of tens of thousands of astronomical units, is weak, so weak that external forces matter. Passing stars matter. The Milky Way matters. The cloud is a sphere because at those distances the Sun is not the only thing pulling. The galaxy itself is part of the story. The sphere is not a structure the Sun built. It is a structure the galaxy shaped. And that tells you something uncomfortable about where the solar system actually ends. Most diagrams of the solar system show the planets in a neat line: Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune. Maybe they include the Kuiper belt as a dotted line beyond Neptune. That is where the diagram stops. The implication is that beyond Neptune, beyond the Kuiper belt, space is empty. Interstellar space begins. The solar system is over. The diagrams are lying. The solar system does not end at Neptune. It does not end at the Kuiper belt. It ends at the Oort Cloud, and the Oort Cloud extends halfway to the nearest star. If you were standing on an object in the outer Oort Cloud, 100,000 astronomical units from the Sun, what would you see? The Sun would not look like the Sun. It would look like a star. Bright, yes, brighter than any other star in the sky. But not a disk, not a glowing circle with visible features. A point of light. You would not feel its heat. The temperature at that distance is a few degrees above absolute zero, the same as the background temperature of the universe itself. The Sun's light would take about a year and a half to reach you. If the Sun exploded, you would not know for a year and a half. You would be so far from the planets, from any solid surface, from anything resembling civilization, that the concept of the solar system would feel abstract, a distant memory. And yet you would still be orbiting, still bound, still falling in an elongated ellipse that would take millions of years to complete. The Sun's gravity, even at that distance, would still own you. That is the prison, not the ecliptic, not the flat plane where the planets live, the sphere, the enormous, invisible bubble of gravitational influence extending outward in every direction until it finally fades into the pull of other stars. The Oort Cloud is the boundary of that bubble. It is the place where the Sun's grip on space weakens enough that other forces start to matter. It is the edge of everything the Sun controls. For most of human history, the idea that the solar system had a boundary would have seemed absurd. The heavens were infinite. The stars were fixed lights on a distant sphere. There was no edge because there was no structure to have an edge. Even after Copernicus and Newton, even after we understood that the planets orbited the Sun and that gravity held them in place, the mental picture of the solar system remained confined to the visible planets. The boundary, if there was one, was wherever the farthest planet happened to be. When William Herschel discovered Uranus in 1781, the solar system doubled in size overnight. When Neptune was discovered in 1846, it doubled again. The Kuiper belt, proposed in the 1950s and confirmed in the 1990s, pushed the boundary outward by another factor of 10. Each time, astronomers assumed they were approaching the true edge. Each time they were wrong. The Oort Cloud is different. It is not just farther out, it is a different kind of structure entirely. It is not a band of objects orbiting in a predictable plane. It is a diffuse shell of debris surrounding everything else. It does not have a sharp edge. It fades gradually into interstellar space. At some point, far enough out, the Sun's gravity becomes so weak that an object's orbit is no longer stable. A nudge from a passing star will pull it free. At that point, the object stops being part of the solar system and becomes part of the galaxy. The boundary is not a line, it is a probability, a gradient, a slow transition from bound to unbound. The Oort Cloud is where that transition happens. The concept of a spherical boundary also forces a reckoning with the language we use to talk about space travel. When people say they want to leave the solar system, what they usually mean is they want to pass Neptune, or maybe the Kuiper belt. But passing Neptune does not mean you have left the solar system. It means you have left the ecliptic groove. You are still inside the sphere, still bound by the Sun's gravity, still technically orbiting. Voyager 1, the farthest human-made object from Earth, is currently more than 160 astronomical units from the Sun. It crossed the heliopause, the boundary where the solar wind gives way to interstellar space, in 2012. That was a significant milestone. It meant Voyager had left the region where the Sun's influence on the local plasma was dominant, but it did not leave the solar system. Not by the definition that includes the Oort Cloud. Voyager is still inside the sphere. It will remain inside the sphere for another 30,000 years. That is how long it will take to cross the Oort Cloud at its current speed of about 38,000 miles per hour. 30,000 years to traverse the outer boundary of the Sun's gravitational prison. By the time Voyager finally exits the Oort Cloud and enters true interstellar space, human civilization, if it still exists, will be unrecognizable. The probe will be a relic from a vanished species, drifting silently past frozen rocks that never knew we existed. The sphere is also a reminder that the solar system is not isolated, it is embedded in the galaxy. The galaxy shapes it, tugs on it, occasionally tears pieces off. When a star passes close to the Sun, close meaning within a light year or two, its gravity does not just nudge Oort Cloud objects, it pulls on everything. The outer planets feel it, the Kuiper belt feels it. The perturbations are tiny, but they accumulate. Over billions of years, the orbits of distant objects shift in ways that have nothing to do with the Sun. The sphere is not just a prison, it is a membrane, a porous boundary where the solar system and the galaxy exchange material. Objects get pulled out of the Oort Cloud and lost to interstellar space. And occasionally objects from interstellar space drift in. Most of them pass through without stopping. But some of them, if their velocity and trajectory happen to align, can be captured by the Sun's gravity. They become part of the Oort Cloud, new members of the sphere, immigrants from another star system entirely. This is not a hypothetical process. We have seen it happen. In 2017, an object appeared in the inner solar system that did not belong. Its orbit was wrong. Its speed was wrong. Its trajectory carried it through the plane of the ecliptic at a steep angle, moving faster than any object bound to the Sun should have been able to move. Astronomers tracked it for a few weeks, calculated its path, and confirmed what the data was screaming. The object had come from outside the solar system. It was not a long-period comet dislodged from the Oort Cloud. It was not a Kuiper belt object knocked into a weird orbit. It was a visitor, an intruder, a piece of debris from another star, passing through our neighborhood on its way to somewhere else. They named it Oumuamua, a Hawaiian word meaning scout or messenger, and its arrival changed the way astronomers think about the space between stars. Because if one interstellar object could find its way into the inner solar system, there had to be others, millions of them, billions, drifting through the galaxy, invisible, untracked, occasionally passing close enough to a star to be noticed. Most of them never get close enough. They stay in the dark, far above or below the ecliptic, where no telescope is looking. The plane is a spotlight, a narrow beam aimed at the thin band where the planets live. Everything outside that beam is a blind spot. And the blind spot, it turns out, is full. The problem with finding something is that you have to be looking in the right direction. That sounds obvious, trivially obvious. But in astronomy, where the thing you are looking for might be smaller than a city block, darker than charcoal, and moving at 30,000 miles per hour through a volume of space so large that human brains cannot meaningfully visualize it, looking in the right direction is not a given. It is a gamble. A statistical bet you make every time you point a telescope at a patch of sky. And for most of the history of astronomy, we have been making the same bet over and over. We have been looking at the ecliptic, the groove, the flat plane where the planets live, because that is where all the action is. That is where the asteroids orbit, where the comets appear, where the planets line up for convenient observation. It made sense. It still makes sense, except it also means that for centuries we have been staring at a narrow band of sky while the rest of the universe drifts past unnoticed, above us, below us, coming in at angles that do not intersect the plane, and we would have kept missing them indefinitely if one of them had not wandered close enough, bright enough, and weird enough to force us to pay attention. On October 19, 2017, a telescope in Hawaii picked up something strange. The telescope was Pan-STARRS 1, a survey instrument designed to scan the sky repeatedly looking for anything that moves, asteroids, comets, anything that was not there the last time the telescope looked at that spot. The object showed up as a faint dot drifting across the field of view. That was normal. Faint dots show up all the time. Most of them are asteroids, some are comets, a few are satellites or space junk that got misidentified. The standard procedure is to measure the object's position over several nights, calculate its orbit, and file it in the database with all the other tracked objects. By the time Pan-STARRS spotted this one, the object was already on its way out of the inner solar system. It had passed closest to the Sun 6 weeks earlier, in early September. It had crossed Earth's orbit on October 14th, 5 days before discovery. The telescope caught it purely by accident during a routine survey sweep. If the timing had been slightly different, if the object had passed through a week earlier or a week later, we would have missed it completely. The astronomers who first looked at the data assumed they were dealing with a comet. The orbit was extremely elongated, which is typical for comets coming from the Oort Cloud. But as more observations came in over the next few days, something did not fit. The orbit was too elongated. The eccentricity, the number that describes how stretched an orbit is, kept climbing. Circular orbits have an eccentricity of 0. Earth's orbit has an eccentricity of about 0.017, which is nearly circular. Most comets from the Oort Cloud have eccentricities close to 1, meaning their orbits are extremely stretched, but still closed, still bound to the Sun. This object's eccentricity was greater than 1. That is not supposed to happen. An eccentricity greater than 1 means the orbit is not an ellipse. It is a hyperbola, an open curve. The object was not orbiting the Sun. It was passing through. It came from somewhere else, swung around the Sun, and was now leaving forever. The realization hit the astronomy community like a brick through a window. This was not an asteroid. It was not a comet. It was an interstellar object, the first one ever confirmed. The first piece of solid matter from another star system that humanity had ever detected. They named it Oumuamua. The name comes from Hawaiian, chosen because the Discovery telescope was in Hawaii. The word roughly translates to scout or messenger, the first to arrive. It fit. Oumuamua was a messenger whether it intended to be or not. It carried information, not a message in the science fiction sense. No alien transmissions, no encoded warnings, just the fact of its existence. Proof that interstellar space is not empty. Proof that objects drift between stars, crossing the galaxy on timescales so long that entire civilizations could rise and fall during a single journey. Proof that if one interstellar visitor could stumble into the inner solar system, there had to be others, millions of them, billions. Most of them invisible, most of them undetected, passing through the dark above and below the ecliptic where no one was looking. Oumuamua was not special because it was rare. It was special because we happened to notice it. The trajectory told the story. Oumuamua came in from the direction of the constellation Lyra, somewhere near the bright star Vega. It entered the solar system from above the ecliptic plane, diving downward at an angle of about 120 degrees relative to the plane. That is steep. Imagine a disk lying flat on a table. Now imagine something falling from the ceiling, passing through the disk at an angle that is almost perpendicular but not quite. That was Oumuamua. It was not moving along the groove, it was cutting through it. The object passed closest to the Sun on September 9th, 2017, coming within about 23 million miles. That is closer than Mercury's orbit. At that distance, if Oumuamua had been a typical comet, it should have started outgassing, heating up, releasing water vapor and dust, forming a coma and a tail. It did not. No coma, no tail, no sign of any activity. Spectroscopic observations showed no evidence of water, ice, or the usual volatile materials that make comets behave like comets. The surface appeared to be dark, reddish, possibly covered in organic material that had been irradiated by cosmic rays during millions or billions of years drifting through interstellar space. Whatever Oumuamua was made of, it was not acting like anything astronomers had seen before. After passing the Sun, the object accelerated slightly. Not because it fired an engine, because the Sun's gravity was flinging it outward. The closer you get to a massive object, the faster you move when you leave. Oumuamua picked up speed as it rounded the Sun, then began the long climb back out of the solar system. By the time astronomers realized what they were looking at, the object was already leaving. It crossed Mars' orbit in early November. It would cross Jupiter's orbit by mid-2018. By 2022, it would be farther from the Sun than Neptune, and it would keep going, out past the Kuiper Belt, out past the Oort Cloud, back into the space between stars. The entire visit, from entering the inner solar system to leaving it, lasted less than a year. A blink, a single pass, and for most of that time, no one on Earth had any idea it was happening. The discovery triggered an explosion of follow-up observations. Every telescope that could be pointed at Oumuamua was pointed at Oumuamua. The object was faint, very faint. It was small, estimated at somewhere between 100 and 400 meters in length, and its surface reflected only about 10% of the light that hit it. That made it roughly as reflective as charcoal. Observations showed that its brightness varied dramatically over the course of several hours, suggesting the object was tumbling end over end in a chaotic rotation. The brightness changes were consistent with an elongated shape, possibly cigar-shaped, though some models suggested it could be more like a flat disk or pancake. The uncertainty came from the fact that no one could resolve the object directly. It was too small and too far away. All the shape information was inferred from how its brightness changed as it rotated. Different shapes produced different light curves, and the light curve from Oumuamua was consistent with something extremely elongated, somewhere between 5 and 10 times longer than it was wide. That was unusual. Most asteroids are lumpy, potato-shaped objects. A few are elongated, but nothing in the solar system looked quite like the models suggested Oumuamua might look. Then the object did something even stranger. It accelerated. Not a lot, not dramatically, but measurably. As Oumuamua moved away from the Sun, it sped up slightly more than gravity alone could account for. The excess acceleration was small, about 0.0001 meters per second, tiny but detectable, and it required an explanation. When comets accelerate as they move away from the Sun, it is because they are outgassing. Jets of gas streaming off the surface push the comet like tiny rocket engines. The effect is well understood and has been observed on every active comet we have ever studied. But Oumuamua showed no signs of outgassing. No coma, no tail, no detectable gas or dust. So what was pushing it? One hypothesis suggested that even a very small amount of outgassing, too faint to detect, could account for the acceleration. Invisible jets of water vapor or carbon monoxide escaping from the surface. Another hypothesis, more exotic, proposed that Oumuamua was being pushed by sunlight itself. Radiation pressure. Photons from the sun bouncing off the object's surface, transferring momentum. For radiation pressure to produce the observed acceleration, the object would have to be extremely thin, less than a millimeter thick in one dimension. A sail, a shard, something more like a sheet of paper than a rock. That hypothesis, championed by Harvard astronomer Avi Loeb among others, led to speculation that Oumuamua might not be a natural object at all, that it might be a piece of technology, a light sail built by another civilization sent on a journey through the galaxy, now tumbling dead through our solar system millions or billions of years after whoever built it ceased to exist. The speculation was controversial. Most astronomers considered it unnecessary. The outgassing explanation, while not perfect, was simpler. It required fewer assumptions. It did not invoke alien engineers, but the radiation pressure idea refused to die because the object's behavior kept resisting easy explanations. The tumbling rotation, the elongated shape, the lack of visible outgassing, the slight, persistent acceleration. None of it was impossible to explain with natural processes, but none of it fit cleanly into any single model. Oumuamua was an outlier, a data point that sat just far enough outside the distribution to make people uncomfortable. By mid-2018, Oumuamua was too faint to observe. It had drifted beyond the reach of even the largest telescopes. The object is still out there, moving away from the Sun at about 58,000 miles per hour relative to the solar system's center of mass. It is heading roughly toward the constellation Pegasus. In about 20,000 years, it will pass within a few light years of another star. In a few million years, it will be so far from the Sun that calling it a visitor to our solar system will feel like a historical footnote, a brief encounter, a moment of proximity in a journey that has no destination. Oumuamua came from somewhere. It is going somewhere else. And everything in between, including us, is just scenery. The object's discovery forced astronomers to confront an uncomfortable truth. If Oumuamua was the first interstellar object we detected, it was not because interstellar objects were rare. It was because we were not looking for them. Pan-stars happened to catch Oumuamua because the object passed close to Earth, and because the telescope was running a survey designed to find anything that moved. Most surveys are not designed that way. Most telescopes stare at the same patches of sky for hours or days, looking for faint, distant galaxies or measuring the properties of known stars. Moving objects, especially fast-moving objects, get filtered out as noise. And even surveys that do look for moving objects are biased toward the ecliptic. That is where the asteroids are. That is where the funding priorities point. You look where you expect to find something because telescope time is expensive and you need to justify every hour. Oumuamua came in from outside the plane. If it had come in along the ecliptic, we probably would have spotted it sooner. If it had stayed farther from the plane, we might have missed it entirely. 2 years later, in August 2019, it happened again. A Crimean amateur astronomer named Gennady Borisov was scanning the sky with a telescope he built himself. He spotted a faint comet that was not in any database. Follow-up observations confirmed that the object was moving on a hyperbolic trajectory. Another interstellar visitor. They named it 2I/Borisov, with the I standing for interstellar. Borisov was easier to understand than Oumuamua. It looked like a comet. It acted like a comet. It had a visible coma and a tail. Spectroscopic analysis showed water vapor, carbon monoxide, and other typical cometary materials outgassing as the object warmed up near the Sun. The composition was consistent with comets from the Oort Cloud, which made sense. Borisov probably formed in another star's equivalent of the Oort Cloud, got ejected by gravitational interactions, and spent millions of years drifting through interstellar space before wandering into our neighborhood. Its trajectory was less steep than Oumuamua's, but still well outside the ecliptic plane. It came in at an angle of about 44 degrees, passed within about 2 astronomical units of the Sun, and left. The entire visit lasted a few months. By mid-2020, Borisov was gone, too faint to track, racing back into the dark. 2 confirmed interstellar objects in 3 years. That does not sound like a lot, but it was enough to let astronomers start doing statistics. If 2 objects passed close enough to Earth to be detected in a 3-year window, how many more must be passing through the solar system undetected? The answer depends on a lot of assumptions. How many interstellar objects are out there in the first place? How fast are they moving? What size range are we talking about? How sensitive are our surveys? The estimates vary, but most models suggest that at any given time there is at least 1 interstellar object closer to the Sun than Jupiter, maybe more. These objects are not stopping, they are not orbiting, they are just passing through, moving too fast for the Sun's gravity to capture them. Most of them are small, most of them are dark. Most of them enter and leave the solar system without ever coming close to Earth or any other planet. We miss them because we are not looking in the right place at the right time. The right place is not the ecliptic. The ecliptic is where we look, because that is where the solar system's permanent residents live. But interstellar objects do not care about the ecliptic. They are not bound by the ancient spin of the protoplanetary disk. They come from random directions, moving on trajectories shaped by the chaotic gravitational environment of wherever they formed and whatever ejected them. If they happen to pass through the ecliptic plane during their transit of the solar system, great, we might see them. If they pass above or below the plane, our odds of detection drop dramatically. Current surveys cover only a fraction of the sky, and most of that coverage is concentrated near the ecliptic. The rest of the sky, the huge swath of space above and below the plane, is a blind spot. Objects moving through that blind spot can pass within a few million miles of Earth and never register on any telescope. The blind spot is not a flaw in the design of our surveys, it is a consequence of limited resources. Telescope time is finite, survey programs have to prioritize, and the ecliptic, for very good reasons, is the priority. That is where near-Earth asteroids live. That is where potentially hazardous objects that could hit Earth are most likely to be found. If you have to choose between scanning the ecliptic for the 1,000th time or scanning a random patch of sky 30 degrees above the plane, you scan the ecliptic. The odds of finding something dangerous, something worth tracking, are higher. The trade-off is that you miss everything that is not moving along the plane. You miss the interstellar visitors. You miss the Oort Cloud comets with highly inclined orbits. You miss rogue planets, if any exist, drifting through on steep trajectories. You miss the universe happening vertically. There is also a geometric problem that makes the blind spot worse. The farther you look from the ecliptic, the farther you are looking through the plane of the Milky Way. The galaxy itself is a disk, and we sit inside that disk. When you look along the plane of the galaxy, you are looking through a lot of stars, a lot of dust, a lot of glowing gas. All of that foreground material makes it harder to see faint, distant objects. Astronomers call this the zone of avoidance. It is the band of sky, roughly aligned with the Milky Way's equator, where observations are difficult because the background is too crowded. If you are trying to spot a faint asteroid or comet, and that object happens to pass through the zone of avoidance, it might get lost in the noise. The light from a million background stars washes it out. The object is there. You just cannot see it. The zone of avoidance does not line up exactly with the ecliptic, but there is overlap. And the overlap means that certain directions are harder to search than others. Objects coming in from the direction of the galactic center or from dense star fields near the Milky Way's plane are more likely to go unnoticed than objects coming from clearer, less crowded regions of sky. The discovery of Oumuamua and Borisov also raised a deeper question. If interstellar objects are passing through the solar system all the time, where are they coming from? Stars do not hold on to their debris forever. Planetary systems eject material constantly. Jupiter and Saturn spent the first few 100 million years of their existence flinging planetesimals out of the solar system at high speed. Most of those objects are now drifting through the Milky Way, billions of miles from the nearest star, cold and dark and invisible. Every star with planets probably went through a similar phase, which means the galaxy is full of this stuff. Trillions of objects, maybe more, wandering through interstellar space. Rocks, ice balls, possibly larger bodies, possibly planets. Rogue worlds that were ejected from their home systems and are now falling through the galaxy on their own. Most of them will never encounter another star. The distances are too large. The galaxy is too empty. But occasionally, by pure chance, one of them passes close enough to a star to be pulled inward, or at least to pass through the star's planetary system on a trajectory that intersects one of the planets. Oumuamua and Borisov were not flukes. They were samples, evidence that the space between stars is not a void. It is full. We just were not looking. The speed of these objects matters too. Oumuamua was moving at about 58,000 miles per hour relative to the Sun when it left the inner solar system. That is fast by human standards. It is not fast by galactic standards. The Sun itself is moving through the Milky Way at about 500,000 miles per hour. Stars in the galaxy have a range of velocities depending on their orbits around the galactic center. An object drifting through interstellar space inherits the velocity of whatever star system it came from, plus whatever velocity it gained when it got ejected, plus any additional velocity it picks up from gravitational interactions along the way. By the time it reaches another star, it could be moving at tens of thousands of miles per hour relative to that star, or it could be moving much slower if it happens to be traveling in roughly the same direction as the star. The relative velocity determines how the encounter plays out. A high-speed encounter means the object zips through the system and leaves. A low-speed encounter means the object lingers, possibly long enough to be captured into an orbit if the geometry is just right. Oumuamua was a high-speed encounter. It came in fast and left fast. Borisov was similar. Neither object was ever at risk of being captured. Their velocities were too high. The Sun's gravity bent their paths but could not hold them. The lack of captured interstellar objects in the solar system is interesting. If interstellar visitors are common, and they have been passing through the solar system for billions of years, why have we not captured any of them? Why is the asteroid belt not full of interstellar rocks? The answer is that capture is hard. It requires a very specific set of conditions. The object has to be moving slowly enough that the Sun's gravity can hold it, but not so slowly that it was already bound to the Sun to begin with. It has to encounter a planet at just the right time, in just the right place, so that the planet's gravity can steal enough of the object's velocity to drop it into a bound orbit, and even then, the captured orbit is usually unstable. Over millions of years, interactions with other planets can eject the object again. Captured interstellar objects probably do exist in the solar system. They are just rare. and they are indistinguishable from native objects unless you do very detailed chemical or isotopic analysis to figure out where they formed. A few asteroids and comets in unusual orbits have been proposed as possible interstellar captures, but none of them have been confirmed. The evidence is circumstantial, suggestive, but not definitive. The broader point is that the solar system is not isolated. It is not a closed box. Material flows in and out on timescales much longer than human history, but much shorter than the age of the solar system. Oumuamua and Borisov are proof of the inflow. The objects Jupiter and Saturn ejected billions of years ago are proof of the outflow. The galaxy is mixing, slowly, randomly, but constantly. And the mixing happens in 3 dimensions, not just along the flat plane of the ecliptic, everywhere. Above, below, from every direction the geometry of space allows. The groove is where we live. The sphere is where everything else happens, and we are only just starting to notice. The next generation of telescopes will help. The Vera Rubin Observatory, currently under construction in Chile, is designed to scan the entire visible sky every few nights. It will not focus exclusively on the ecliptic. It will look everywhere, cataloging everything that moves, everything that changes, everything that was not there the last time the telescope looked. When it comes online, the rate of interstellar object discoveries is expected to increase dramatically. Some estimates suggest Rubin could detect 1 interstellar visitor per year, maybe more. Each detection will add another data point to the distribution. Another piece of information about what is drifting through the galaxy and how often it passes through our neighborhood. Over time, the statistics will sharpen, the blind spot will shrink, not because we will have better technology, though we will, but because we will finally be looking in the right places, and the right places are not in the groove. They are above it, below it, perpendicular to it. Everywhere we were not looking before because we assumed nothing was there. Oumuamua taught us that assumption was wrong. The messenger arrived. The message was simple. The space above and below the ecliptic is not empty. It is full of things we have been missing. Things that do not orbit like planets. Things that do not care about the ancient spin of the protoplanetary disk. Things that come from other stars, other systems, other corners of the galaxy. And some of those things are not small rocks tumbling through the void. Some of them are larger, much larger. Worlds without stars. Planets that were born in orbit around a sun and then lost that orbit, ejected into the dark, falling through the ceiling of the ecliptic plane with nothing to slow them down and nowhere to land. Rogue worlds. And they are out there right now, drifting through the blind spot, waiting for someone to notice. There is a category of object drifting through the galaxy that makes Oumuamua look quaint. Not a rock, not a comet, not a chunk of frozen debris tumbling through the void. A planet, a full planet. Worlds the size of Earth, the size of Jupiter, some of them possibly larger, moving through interstellar space with no star to orbit, no sun to warm them, no gravitational anchor to keep them in place. They are called rogue planets, though that name makes them sound romantic, like pirates or outlaws. The reality is darker. These objects were not born free. They were ejected, thrown out of their home systems by gravitational violence, cast into the cold and left to wander the galaxy alone. And they are everywhere. Billions of them, possibly trillions. Drifting through the Milky Way like ghosts, silent and invisible, moving on trajectories that obey no pattern because they were shaped by chaos. Most of them will never encounter another star. They will spend the rest of eternity falling through empty space, cooling slowly, their surfaces frozen, their atmospheres collapsed into ice, their cores the only remaining source of heat. But some of them, A tiny fraction will pass close enough to another star system to interact with it, to disturb it, to alter the orbits of planets that have been stable for billions of years, and we would not see them coming. The concept of a rogue planet is not new. Astronomers have been discussing the possibility since the mid-20th century. If planets can form around stars, and if those planets can be kicked out of their systems by gravitational interactions, then interstellar space should be full of them. The logic is airtight. What took decades was finding one, because a planet without a star is nearly impossible to detect. It does not shine. It does not reflect light from a nearby sun, because there is no nearby sun. It is a dark object, possibly smaller than Earth, moving through a volume of space so vast that the odds of it passing in front of a background star are negligible. For most of the history of astronomy, rogue planets were a theoretical prediction with no observational evidence. Scientists knew they should exist, they just could not prove it. That changed in the last 2 decades as detection methods improved and surveys began covering larger areas of sky with greater sensitivity. The first confirmed detections came from gravitational microlensing, a technique that uses the gravity of a foreground object to magnify the light from a background star. If a rogue planet drifts between Earth and a distant star, its gravity bends the starlight, creating a brief brightening that lasts a few hours to a few days. The event is rare, temporary, and unrepeatable. You get one chance to measure it. If you miss it, it is gone. By the early 2000s, microlensing surveys had found a handful of candidate rogue planets, objects with masses ranging from a few times Earth's mass to several times Jupiter's mass, all of them drifting alone through the galaxy with no parent star in sight. The real breakthrough came when astronomers started to understand how common these objects were. Early estimates based on microlensing event rates suggested there might be as many rogue planets in the Milky Way as there are stars. 200 billion stars, 200 billion rogue planets. That estimate has been revised upward. More recent models, extrapolating from better data and more sophisticated simulations of planetary system formation, suggest the true number could be much higher, trillions. Some estimates go as high as 20 rogue planets for every star in the galaxy. If that is accurate, rogue planets outnumber stars by a factor of 20 to 1. The galaxy is not mostly stars. It is mostly dark, wandering worlds that no one will ever visit, no one will ever name, and no one will ever see. The Milky Way is a graveyard of planets, and we live inside it. How does a planet become rogue? The most common pathway is gravitational scattering. Picture a young planetary system, a few million years old. The star has just finished forming. The protoplanetary disk is clearing. Planets are assembling, colliding, merging, growing. The system is crowded. Multiple planetary cores are competing for the same material. Orbits are crossing. Close encounters happen constantly. When 2 planets pass close to each other, their mutual gravity changes both of their orbits. One planet gets accelerated, gaining orbital energy. The other gets decelerated, losing energy. The planet that gains energy moves outward into a higher, more elongated orbit. The planet that loses energy moves inward, closer to the star. If the encounters continue, if the system remains unstable, the process repeats. One planet keeps getting kicked outward, its orbit stretches. Eventually, it stretches so far that the planet is barely bound to the star. One more encounter, one more gravitational kick, and it is gone. Ejected, unbound, moving fast enough that the star's gravity can no longer hold it. The planet becomes a rogue. Simulations of this process, run thousands of times with different initial conditions, show that ejections are not rare, they are common. In systems with multiple large planets, especially gas giants, the odds of at least one planet getting ejected are high. Some simulations suggest that 90% of the objects in unstable systems eventually get thrown out. Not 90% of systems, 90% of objects in those systems that do not stabilize. Most of those objects are smaller bodies, planetesimals, asteroids, comets, but a significant fraction are planets, full-sized worlds that spent millions of years forming only to be thrown away before they had a chance to settle into a stable orbit. Our own solar system probably ejected planets. The NICE model, a widely accepted theory of the solar system's early history, proposes that Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. They started closer together in more compact orbits. Then, a few 100 million years after the Sun formed, something triggered an instability. The planets began migrating. Jupiter moved inward slightly, Saturn moved outward. Uranus and Neptune were scattered outward dramatically, plowing through the primordial Kuiper belt and flinging debris in every direction. Some of that debris fell inward, bombarding the inner planets during a period called the Late Heavy Bombardment. Some of it was ejected entirely, cast into the Oort Cloud or out of the solar system altogether. And some models suggest there may have been a fifth giant planet, an ice giant similar to Uranus or Neptune, that got caught in the chaos and ejected. If that planet existed, it is out there now, somewhere in the Milky Way, drifting alone, a sibling world we will never meet, unbound, forgotten, lost. There is another formation pathway that is even stranger. Some rogue planets may never have orbited a star at all. In the densest regions of star-forming clouds, where thousands of stars are being born in close proximity, the environment is gravitationally chaotic. Collapsing gas clouds can fragment into multiple cores. Some of those cores are massive enough to become stars. Others are smaller, below the threshold for hydrogen fusion. They become brown dwarfs, objects that are too big to be planets but too small to be stars. And some fragments are even smaller, planetary mass objects that form in isolation, never accreting onto a star, never entering orbit around anything. These objects are born rogue. They are planets by mass, but they form like stars, condensing directly out of a gas cloud. Astronomers call them free-floating planetary mass objects, a mouthful of a name that reflects the ambiguity of what they actually are. Planet or failed star. The line blurs. What matters is that they exist, and they add to the population of dark objects drifting through interstellar space. In 2025, the European Southern Observatory announced something remarkable: a rogue planet, designated SHA 1107-7626, about 620 light-years away in the constellation Chamaeleon, was caught in the act of growing, not orbiting a star, not sitting quietly in the dark, actively accreting gas and dust at a rate of about 6 billion tons per second. The object had a mass estimated at 5 to 10 times Jupiter's mass, and it was behaving like a young star. Material was falling onto it, heating up, glowing in infrared. The discovery shattered the assumption that rogue planets are dead, inert objects. This one was alive, still feeding, still growing, possibly still in the process of forming. The accretion rate was described as record-breaking, the fastest ever measured for any planet. The researchers pointed out that the line between planet and brown dwarf, already fuzzy, was getting fuzzier. If a planetary mass object forms in isolation and accretes material the way stars do, is it still a planet? Does the formation mechanism matter more than the final mass? Nobody has a clean answer. What everyone agrees on is that the object exists, and it is not unique. If one rogue planet is accreting, Others probably are too. The galaxy is full of these things, and we are only just starting to notice them because we are finally looking in the right part of the spectrum. Infrared, heat, the faint glow of objects that are not quite cold yet. Most rogue planets are cold, extremely cold. Without a star to warm them, the only heat they have is whatever is left over from their formation and whatever their cores generate through radioactive decay or residual compression. For a planet the size of Earth, that heat is minimal. Surface temperatures would drop to a few dozen degrees above absolute zero within a few million years. Any atmosphere would freeze out, condensing onto the surface as ice. Any oceans would freeze solid. If the planet had life, that life would die, unless it was deep underground near geothermal vents where the planet's internal heat could sustain it. A rogue Earth would not be habitable on the surface. It would be a frozen ball, darker than charcoal, drifting through the void. A gas giant, on the other hand, retains heat longer. Jupiter, for example, radiates more energy than it receives from the Sun. Its core is still hot from the planet's formation, and the slow contraction of its interior generates additional heat. A rogue Jupiter would cool over billions of years, but it would stay warm enough to glow faintly in infrared for much of that time. Its atmosphere would not freeze, its clouds would keep churning. From a distance, you would not be able to see it in visible light, but infrared telescopes would pick it up as a faint, warm blob. That is how most rogue planets are found, by their heat, by the faint infrared signature that marks them as objects that are slightly warmer than the cosmic background. The difficulty of detection cannot be overstated. A rogue planet the size of Earth, cooled to background temperature, sitting a few light years away, is effectively invisible. It does not emit light. It does not reflect light. It is not blocking any stars because the odds of it lining up perfectly between Earth and a background star are astronomically low. The only way to find it is if it passes close enough to something bright that its gravity causes a measurable effect. Microlensing, gravitational distortion, a brief temporary signal that tells you something massive passed through your line of sight. The problem is that microlensing events are rare, short-lived, and require continuous monitoring of millions of stars. Current surveys detect a few dozen microlensing events per year. Only a fraction of those are caused by rogue planets. Most are caused by stars, brown dwarfs, or other objects that are easier to characterize. Scaling up from the detected events to estimate the total population of rogue planets involves layers of assumptions. How many planets are too small to cause detectable lensing? How many are moving too fast or too far from any bright stars to be noticed? How many are passing through regions of the galaxy that no survey is monitoring? The uncertainty is enormous. The numbers could be off by a factor of 10 in either direction. But even the conservative estimates suggest billions of rogue planets in the Milky Way. And the aggressive estimates suggest we are surrounded by them. Which brings us to the nightmare scenario. What happens if a rogue planet passes through the solar system, not hits the Earth, not collides with the Sun, just passes through, enters from above or below the ecliptic, crosses the orbital plane, disrupts a few things with its gravity, and leaves? The odds of this happening in any given year are vanishingly small. One estimate puts the chance of a rogue planet entering the solar system in the next 1,000 years at about 1 in a billion. Those are lottery odds. Worse than lottery odds. You are more likely to be struck by lightning while holding a winning lottery ticket than to witness a rogue planet wandering through the solar system during your lifetime. But the solar system is 4.5 billion years old. Over that time scale, the improbable becomes inevitable. It has probably happened before. It will probably happen again. The question is not if, but when. and what the consequences would be. A rogue planet does not need to hit anything to cause damage. Its gravity is enough. Gravity does not care whether objects are touching. It acts at a distance. A planet the size of Jupiter passing through the outer solar system, say a few hundred astronomical units from the Sun, would gravitationally perturb every object it came near. Kuiper belt objects would have their orbits shifted. Some would be thrown inward toward the planets. Others would be ejected entirely, turned into rogue objects themselves. The effect would cascade. Objects whose orbits were stable for billions of years would suddenly be unstable. Close encounters would become more common. Collision rates in the inner solar system would spike. Earth would experience an uptick in asteroid impacts, possibly lasting millions of years, as the perturbed objects slowly filtered through the inner solar system. Not an extinction event overnight, a gradual increase in chaos. If the rogue planet passed closer, the effects would be more dramatic. A Jupiter mass object passing within a few tens of astronomical units of the Sun could perturb the orbits of the outer planets. Neptune's orbit could shift slightly. Uranus could be nudged into a more eccentric path. Those changes would ripple inward over thousands of years, destabilizing the resonances that keep the inner solar system stable. Earth's orbit could shift, not by much, maybe a few million kilometers, but that is enough to change the amount of sunlight reaching the surface, enough to alter the climate, enough to tip the planet into an ice age or a warming period, depending on which direction the shift goes. The change would not be instantaneous. It would unfold over millennia. But the cause would be a single close encounter with an object that no one saw coming because it was dark, cold, and moving perpendicular to the plane where everyone was looking. The rogue planet would continue on its way, unaffected, leaving behind a solar system that was subtly, irrevocably different. By the time astronomers figured out what had happened, the intruder would be gone, 1 billion miles away. Untraceable, a ghost. There is a deeper horror buried in this scenario, the possibility that a rogue planet has already passed through the solar system. Recently, within the last few thousand years, and we missed it. How would we know? What evidence would it leave? If it did not collide with anything, if it only perturbed a few distant orbits, the changes would be subtle. Too subtle to notice without detailed models of the solar system's long-term dynamics. Astronomers do have those models now. They can simulate the orbits of planets millions of years into the past and future, looking for anomalies, checking whether the current configuration is stable or slowly drifting toward instability. Most of those models suggest the solar system is stable. The planets are where they should be. Their orbits have not been disturbed recently, but the models are not perfect. They rely on measurements of planetary positions that are only a few centuries old. Anything that happened before telescopes, before accurate astronomical records, is invisible to us. A rogue planet passing through 3,000 years ago would leave no trace we could detect today. The orbits would have had time to settle. The perturbed Kuiper belt objects would have either collided with something or drifted into new stable orbits. The evidence would be gone, erased by time. We would never know it happened. The cosmic horror is not the collision, it is the invisibility. The idea that something the size of a planet, something with enough gravity to reshape the solar system, could pass within spitting distance of Earth and remain undetected until it was too late to do anything. Oumuamua scared people when it was discovered, not because it was dangerous, but because it was small and we almost missed it. A rogue planet would be worse, larger, more massive, easier to detect if you were looking in the right place, but almost impossible to spot if you were not. Current surveys are not designed to find rogue planets entering the solar system. They are designed to find asteroids, small, fast-moving objects in the ecliptic plane. A rogue planet coming in from above or below the plane, moving at tens of kilometers per second, would not trigger most of the automated detection systems until it was already inside the orbit of Neptune. By then, weeks would remain before closest approach, maybe months if we were lucky, decades if we were very lucky. Not enough time to do anything except watch and measure and hope it did not come too close. Detection would require infrared telescopes scanning the sky continuously, looking for faint warm objects moving against the background. The James Webb Space Telescope could do it in theory, but Webb is not a survey instrument. It stares at tiny patches of sky for hours at a time, studying individual objects in exquisite detail. It is not sweeping the sky looking for anything that moves. Ground-based infrared surveys could do it, but most of them are focused on mapping the Milky Way, studying star formation, characterizing exoplanet atmospheres. Finding rogue planets is a secondary goal at best. The Vera Rubin Observatory, when it comes online, will help. It will scan the entire visible sky every few nights, cataloging everything that changes position. If a rogue planet enters the solar system and happens to pass through the survey area, Rubin will find it, eventually. The question is whether eventually is soon enough, and whether the object is bright enough, invisible or infrared, to stand out against the background noise. A cold rogue Earth would not be bright enough. Rubin would miss it. Only infrared surveys would have a chance, and even then, only if the planet passed relatively close to the Sun, close enough to warm up slightly, close enough to glow. There is also the possibility that rogue planets are more common in the solar neighborhood than the galactic average. The Sun is moving through the Milky Way at about 500,000 miles per hour, passing through different regions of the galaxy as it orbits. Some regions are denser than others. Some have more stars, more planetary systems, more opportunities for gravitational scattering events that create rogue planets. If the Sun is currently passing through a region with a higher density of rogue planets, the odds of an encounter go up, not dramatically. The space between stars is still enormous. But slightly higher odds, compounded over millions of years, could mean the difference between an encounter every billion years and an encounter every few 100 million years. We do not know which kind of region we are in right now. We do not have a detailed enough map of rogue planets to say whether the local density is high or low. We are flying blind. Again, the same blind spot that hid Oumuamua and Borisov is hiding rogue planets. Objects moving perpendicular to the plane, coming from directions we are not watching, arriving without warning. And then there is the question of what a rogue planet looks like up close. Nobody knows. We have never seen one in detail. The detections we have are statistical inferences, micro-lensing events that tell us something massive passed by, but do not tell us what it looked like. An Earth-sized rogue planet, frozen for billions of years, would probably look like a darker, colder version of Pluto. A surface covered in nitrogen ice, methane ice, water ice, no atmosphere, no weather. Just a ball of frozen rock and ice drifting through the void. A Jupiter-sized rogue planet would still have an atmosphere. Thick clouds of hydrogen and helium, possibly ammonia and methane, depending on how warm the planet still is. The clouds would be dark, not lit by any sun, glowing faintly in infrared from the heat radiating out of the interior. From a distance it would look like a dim ember. Up close it would look like Jupiter, but darker, quieter, no lightning, no auroras, just the slow churn of an atmosphere with nowhere to go. If the planet still had moons, and it might, those moons would be frozen too. Dark chunks of ice orbiting a dark planet, invisible except for the faint heat signature. A system in miniature, unmoored, traveling through interstellar space as a unit. planet and moons together. A family of exiles. Some scientists have speculated that rogue planets could harbor life. Not on the surface. The surface would be uninhabitable. But deep underground, or deep in the ocean if the planet is large enough to have a liquid water ocean beneath a thick ice crust, geothermal heat could sustain ecosystems, life that never sees sunlight, life that evolved in the dark and stayed in the dark even after the planet was ejected. If Earth were turned into a rogue planet tomorrow, life in deep ocean hydrothermal vents might survive. The surface would freeze, the oceans would ice over. But kilometers below the ice, where volcanic vents pump heat and chemicals into the water, extremophiles could persist. They would not know the sun was gone. Their environment would remain unchanged. Over millions of years, the planet would cool, the vents would die, and the ecosystem would collapse. But for a while, life would continue, alone, in the dark, orbiting nothing. The idea is haunting. Entire biospheres drifting through interstellar space, sealed inside frozen worlds, unaware that they are no longer home, that their planet is no longer a planet in the traditional sense, just a rock with a hot core falling through the galaxy forever. The broader implication is that the galaxy is more dynamic than we give it credit for. Stars are not fixed. Planets are not fixed. The neat diagrams we draw of solar systems with planets in stable orbits around central stars are snapshots, temporary configurations. On long enough timescales, everything moves, everything gets scattered. Stars eject planets, planets eject moons, moons eject smaller debris. The galaxy is full of this material, all of it drifting, all of it moving on trajectories that were set millions or billions of years ago by gravitational encounters that no one witnessed and no one recorded, and occasionally those trajectories intersect. A rogue planet crosses a star system. A star passes through a planetary system. The Oort Cloud gets disturbed. Comets rain inward, orbits shift. The system that looked stable yesterday is chaotic today. The groove, the flat plane where the planets orbit, is only stable because nothing has disturbed it recently. But recently is a human timescale. On geological timescales, on astronomical timescales, disturbances are routine. The question is not whether the next disturbance will happen. The question is when, and whether it will come from the plane or from somewhere else, somewhere above, somewhere below, somewhere we are not looking. A rogue planet falling through the ceiling, silent and invisible, bringing chaos with it. And by the time we notice, it will already be here. The rogue planets are a warning, not just of what could happen, but of what we are still missing. The galaxy is full of invisible things moving on trajectories we do not track, coming from directions we do not monitor, carrying enough mass to reshape a solar system without ever touching it. And the reason we are missing them, the reason we missed Oumuamua until it was already leaving, the reason we would miss a rogue planet until it was too close to ignore, comes down to the same problem we have been circling for the last 6 chapters. We are trapped in the groove, the ecliptic plane. The ancient, flat band of space carved out 4.5 billion years ago when a cloud of gas collapsed into a spinning disk and everything we now call the solar system condensed out of that disk. The planets orbit in the groove, the asteroids orbit in the groove. Our spacecraft travel in the groove because fighting your way out of it costs more energy than most missions can afford. And our telescopes, the instruments we use to map the universe, spend most of their time staring at the groove because that is where the action is. That is where the planets live, where the near-Earth asteroids drift, where the comets appear. The groove is home. The groove is the map. The groove is the solar system as we understand it. And the groove is a lie. not in the sense that it does not exist. It exists. You are sitting in it right now, moving at 67,000 miles per hour, in a direction you will never feel, never see, never escape without spending a lifetime's worth of fuel to cancel out the motion you inherited the day you were born. The lie is the assumption that the groove is all there is, that the flat plane where the planets orbit is the solar system, and everything outside that plane is just empty space, interstellar void, nothing worth looking at. The discoveries of the last few decades have shattered that assumption, one data point at a time. The Oort Cloud is not flat. It is a sphere wrapping around the solar system in every direction, extending outward to distances so enormous that sunlight takes more than a year to cross it. Interstellar objects like Oumuamua and Borisov do not respect the ecliptic. They come in from above and below, cutting through the plane at steep angles, moving too fast to be captured, too faint to be seen, until they are almost past us. Rogue planets drift through the galaxy on paths that have nothing to do with any star's equator or any ancient protoplanetary disk. They move through the vertical, the up and down. The dimension we are only just beginning to understand is not empty, it is full. And we have been ignoring it because looking up costs more than looking sideways, because leaving the plane requires energy we do not have, technology we have not built, and a willingness to spend decades on a mission that might not return anything more valuable than a new data point. The vertical is not a mystery because we lack the physics. We understand orbital mechanics. We understand gravity. We know exactly how much delta V it would take to climb out of the ecliptic and park a spacecraft a few thousand astronomical units above the Sun, where it could look down at the solar system from outside the plane, mapping the structure of the Oort Cloud, watching for rogue planets, scanning the blind spot that current surveys cannot reach. The math is not the problem. The problem is that the math says it is expensive, prohibitively expensive. Chemical rockets cannot do it, not without staging so many boosters that the whole enterprise becomes absurd. You would need a rocket the size of a building to lift enough fuel to lift the spacecraft. The tyranny of the rocket equation strikes again. Every kilogram of payload requires multiple kilograms of fuel, and every kilogram of fuel adds mass, which requires more fuel, which adds more mass, spiraling outward until the numbers stop making sense. The only reason Ulysses succeeded was Jupiter, the gravity assist, the trick where you borrow momentum from a planet and use it to redirect your trajectory without burning fuel. Ulysses launched on a normal rocket, flew to Jupiter, swung around the planet's south pole, and came out the other side, moving at an 80-degree angle to the ecliptic. The entire mission cost about $1.3 billion in 1990 money, adjusted for inflation that is about $2.5 billion today. Not cheap, but doable. A single mission, carefully planned, using a technique that had been proven by Voyager a decade earlier. It worked, and then we never did it again. There have been proposals, concepts, white papers written by scientists who want to go back, who want to build a better Ulysses with modern instruments, faster data transmission, closer passes to the Sun, higher inclination. None of them have been funded. Not because the science is not good. The science is excellent. A polar solar observatory would revolutionize our understanding of the Sun's magnetic field, the solar wind, space weather, the whole chaotic mess of plasma and radiation that fills the heliosphere. But the cost is high, the timeline is long, and the political appetite for missions that take 4 years just to reach the starting line is limited. Funders want results. They want images. They want discoveries that can be explained in a press release and celebrated in a headline. A probe that spends a decade looping above and below the Sun, measuring particle densities and magnetic field strengths, does not generate the kind of public excitement that keeps budgets flowing. It generates data, enormously valuable data. Data that changes textbooks and refines models and answers questions that have been open for half a century. But data does not photograph well, and missions that do not photograph well struggle to survive the budget process. So the vertical remains mostly unexplored. Ulysses gave us a glimpse. A single spacecraft, a single orbit, a single set of instruments sampling the solar wind from high latitudes during 2 passes over each pole across 18 years of operation. That data is still being analyzed. Papers are still being published using Ulysses measurements as a baseline, comparing them to newer observations from spacecraft in the ecliptic plane, trying to build a 3-dimensional picture of the heliosphere from 2-dimensional snapshots and one narrow slice through the vertical. It is like trying to map an ocean by dragging a single sensor through the water on a fishing line and then extrapolating what the entire ocean must look like based on that one path. You get information, you get hints, you do not get the full picture. The full picture requires coverage. Multiple spacecraft at different latitudes, different distances, different phases of the solar cycle. A constellation of probes scattered above and below the plane, all talking to each other, all feeding data back to Earth, building a real-time map of the Sun's influence in 3 dimensions. That mission has been proposed multiple times, under different names, with different instrument suites. It has never been funded, not fully, not enough to actually build the hardware and launch it. Because the cost is not 1 Ulysses, it is 5 or 6 or 10 Ulysses missions, and nobody has that kind of budget lying around. The same problem applies to mapping the Oort Cloud. We know it is there, we know it is a sphere, we know it contains trillions of objects, most of them small, some of them large, all of them frozen, all of them drifting in the dark at distances so enormous that the sun is just a bright star. But we have never seen it, not directly. Every Oort Cloud object we have ever identified was a comet that fell inward, crossed the inner solar system, and got catalogued during its brief passage through the region where our telescopes can actually see things. The cloud itself, the vast spherical shell of debris surrounding everything we think of as the solar system, is invisible. It is too far away. The objects are too faint, and we are looking at it edge-on from inside the plane, which is the worst possible angle. Imagine trying to map the surface of a soccer ball by standing at the exact center and looking outward. You can see the parts of the ball directly in front of you and directly behind you. The top and bottom are hidden. The sides are foreshortened. You are getting the least useful perspective possible. That is where we are. That is where we have always been. Inside the groove, looking outward, seeing only the thin band of sky that lines up with the ecliptic. To actually map the Oort Cloud, you would need to get outside it, or at least significantly above or below it, far enough that you could look back at the solar system from a different angle and start picking out the faint, distant objects that make up the shell. No spacecraft has ever done that. Voyager 1 is farther from the Sun than any other human-made object, but it is still inside the plane. Its trajectory carries it slightly above the ecliptic, but not by much, a few degrees. Enough to say it left the groove in a technical sense, but not enough to give it a different view. From Voyager's perspective, the solar system still looks like a flat disk. The ecliptic dominates, the vertical is still hidden. To break that perspective, you would need a mission designed specifically to climb, to cancel out the sideways motion, redirect into a polar trajectory, and coast outward for decades until you were far enough from the plane that the geometry shifted. That mission does not exist. It has never been seriously funded. The closest anyone has come is a concept called the Interstellar probe. a spacecraft designed to travel faster and farther than Voyager, reaching 1,000 astronomical units within 50 years. The probe would carry instruments to study the heliosphere boundary, the interstellar medium, the local environment outside the Sun's immediate influence. Some versions of the mission profile include a trajectory that climbs out of the ecliptic, not by a lot, maybe 20 or 30 degrees, but enough to sample a different slice of space than Voyager did. The mission is still in the concept phase. It has not been approved, it has not been built. And even if it launches tomorrow, it would not reach 1,000 astronomical units until the 2070s, 50 years. 2 generations. By the time the data comes back, the people who designed the mission will be retired or dead. That is the time scale we are talking about when we talk about exploring the vertical. Not years, decades, lifetimes. There are faster options in theory: nuclear propulsion, ion drives, solar sails, technologies that do not rely on chemical rockets and their miserable fuel efficiency. A spacecraft powered by a nuclear reactor could accelerate continuously for months or years, building up speed far beyond what chemical rockets can achieve. An ion drive uses electricity to accelerate ions out of a thruster at extremely high speeds, generating thrust that is tiny but constant. Over time, the velocity adds up. A solar sail uses the pressure of sunlight itself to push a spacecraft. No fuel required, just a large reflective surface and patience. All of these technologies exist. All of them have been tested. Some of them have flown on actual missions. The Dawn spacecraft used an ion drive to visit the asteroid Vesta and the dwarf planet Ceres. The Japanese probe Icaros deployed a solar sail and successfully demonstrated controlled flight using radiation pressure. NASA's Parker solar probe, currently diving closer to the Sun than any spacecraft in history, relies on a heat shield and careful orbital mechanics, but future versions of the concept could incorporate ion drives or other advanced propulsion to extend the mission profile. The technology is real. It works. It is just not fast enough, not powerful enough to make vertical exploration cheap or easy. Even with advanced propulsion, leaving the ecliptic is expensive. You are fighting inertia. You are fighting the 67,000 miles per hour of sideways motion that you inherited from Earth, that Earth inherited from the Sun, that the Sun inherited from the collapsing gas cloud that formed the solar system. All of that momentum is pointed in one direction, sideways. To go vertical, you have to spend energy cancelling out that sideways momentum and redirecting it. The more you want to redirect, the more energy you need, and energy translates into fuel, or reactor mass, or sail area, or time. There is no free lunch. Every trajectory costs something. The cheapest trajectory is the one that stays in the plane. The most expensive is the one that leaves it. We have chosen cheap for the last 60 years because cheap is what we can afford. Cheap gets you to Mars. Cheap gets you to Jupiter. Cheap gets you to Saturn, Uranus, Neptune, the Kuiper Belt. Cheap has given us an extraordinary catalogue of knowledge about the solar system's equator. But cheap has not taken us above or below. Cheap has not shown us what the solar system looks like from outside the groove, and as long as cheap remains the only option, the vertical will remain the undiscovered country. There is also the question of what we would do if we got there. What instruments would you put on a spacecraft designed to explore the vertical? What science questions are we trying to answer that cannot be answered from the ecliptic? The obvious answer is mapping the Oort Cloud, finding rogue planets, detecting interstellar objects before they cross the inner solar system, studying the heliosphere's shape and boundaries in 3 dimensions, measuring cosmic rays, solar wind, magnetic fields at high latitudes over long timescales. All of that is valuable. All of that would advance our understanding. But would it advance it enough to justify the cost? That is the question every mission proposal has to answer. Science is not free. Spacecraft are not free. Launch vehicles, mission operations, data analysis, all of it costs money, and money is finite. Agencies have to prioritize. Do you spend $2 billion on a vertical solar probe, or do you spend that same $2 billion on a lander for Europa, a sample return from Mars, a next-generation space telescope? Every mission that gets funded means 10 other missions do not. Every yes is 100 no votes. And the vertical, for all its mystery, for all the blank spaces on the map, has not yet made the case that it is more important than the targets we can reach more easily. That calculus could change. If we detect a rogue planet heading toward the inner solar system, the vertical suddenly becomes urgent. If long-period comets start arriving at unexpected rates, suggesting something in the Oort Cloud has been disturbed, mapping the cloud becomes a priority. If space weather models keep failing because we do not understand the Sun's polar regions well enough, a new polar mission becomes necessary. The vertical is not important until it is. And by the time it becomes important, by the time we need the data, it will be too late to launch the mission that collects it. Spacecraft take years to build, decades to reach their destinations. The knowledge gap we are ignoring today could become the crisis we cannot solve tomorrow. That is the uncomfortable truth buried in all of this. We are flying blind in a dimension we have barely explored, gambling that nothing important will happen there before we get around to looking. And the dimension is huge. When people picture the solar system, they picture the ecliptic, a flat disk with the sun in the middle and planets spread out in neat circles. That image is everywhere. Textbooks, websites, planetarium shows. It is the default mental model. But the real solar system is not a disk, it is a sphere. The Oort Cloud alone extends upward and downward from the plane by tens of thousands of astronomical units. The volume of space above and below the ecliptic dwarfs the volume inside it. If you calculated the total three-dimensional volume contained within the Oort Cloud's outer boundary and compared it to the volume of the thin disk where the planets orbit, the disk would be a rounding error, a sliver, a line drawn through the center of an enormous bubble. We live on the line. We have explored the line. We have sent spacecraft up and down the line, visiting every major planet, dozens of moons, hundreds of asteroids, a handful of comets. We have mapped the line in exquisite detail, and we have barely glanced at the bubble. The vertical is not a footnote. It is the majority of the space we claim to inhabit, the majority of the solar system's volume, the majority of the region where the sun's gravity still dominates. And we have ignored it because it was hard to reach, and we had other priorities. The philosophical weight of that realization is heavy. For most of human history, we thought we were the center of everything. The Earth was the center of the cosmos. The sun and stars revolved around us. Then Copernicus moved us out of the center and put the sun there instead. Then Hubble showed us that the sun was just one star among billions in a galaxy that was itself just one galaxy among billions. Every step has been a demotion, a realization that we are smaller, less significant, more isolated than we thought. The vertical is another demotion, not of humanity's place in the universe, but of our understanding of the neighborhood we live in. We thought we knew the solar system. We thought we had mapped it, catalogued it, understood its boundaries. The discovery of the Oort Cloud, the realization that interstellar objects pass through constantly, the detection of rogue planets drifting through the galaxy, all of it has expanded the map faster than we can explore it. The solar system we live in is larger, stranger, and more dynamic than the diagrams suggest. And most of it is vertical. Most of it is out of the plane. Most of it is space we have never visited, objects we have never seen, phenomena we have never measured. The groove is home, the sphere is everything else, and we are only just starting to understand that the sphere exists. Looking forward, the question is whether we will ever truly explore the vertical or whether it will remain a blank space on the map indefinitely. The technology exists. The science case is strong. What is missing is the will, the funding, the cultural momentum that turns concepts into hardware and launches them into space. That momentum has to come from somewhere. Maybe it comes from a crisis. A rogue planet detected heading toward the inner solar system, forcing an urgent mission to intercept and study it. A solar storm originating from the polar regions that disrupts satellites and power grids, proving we need better observations from high latitudes. A long-period comet that arrives without warning, coming in from a direction no survey was monitoring, demonstrating that the blind spot is a real vulnerability. Crises focus attention, they unlock budgets, they make the impossible suddenly necessary. Or maybe the momentum comes from ambition. A space agency decides that mapping the Oort Cloud is a generational goal, a project worth pursuing even if the results will not arrive for 50 years. A billionaire with a space company decides that leaving the Ecliptic is the next frontier and funds a mission out of pocket. A coalition of nations agrees that understanding the heliosphere in 3 dimensions is important enough to split the cost and build a constellation of probes. Ambition has driven exploration before. It could drive it again, or maybe the momentum never comes. Maybe the vertical remains unexplored because we never find a reason urgent enough or exciting enough to justify the cost. Maybe we spend the next century sending probes to Mars, building bases on the Moon, mining asteroids in the plane, exploring the Kuiper Belt, and never once looking up. That is possible, likely even. The path of least resistance is powerful. The groove is comfortable. It has delivered results for 60 years. It will keep delivering results as long as we keep following it. And if the cost of following the groove is that we miss what is happening in the vertical, well, we have been missing it for this long. What is another century? The rogue planets will keep drifting. The Oort Cloud will keep shedding comets. Interstellar objects will keep passing through unnoticed. The solar system will remain a sphere that we treat like a disk. And the ceiling, the true spatial limit of our understanding, will stay where it has always been, just out of reach, just expensive enough to ignore, just uncertain enough to postpone. The undiscovered vertical will remain undiscovered, not because we cannot reach it, but because we choose not to. Because the cost is too high, and the timeline is too long, and the return is too abstract. Because we are creatures of the plane, locked into the groove by momentum, by history, by the simple fact that everything we have ever built was designed to move sideways, and breaking that pattern, turning 90 degrees and climbing out of the disk into the vast unknown above and below, requires more than technology. It requires a willingness to spend decades on a question whose answer might not matter until long after we are gone. It requires faith that the knowledge is worth pursuing even if the people who pursue it never see the destination. It requires accepting that some frontiers are not conquered in a single lifetime. Some discoveries take generations. Some maps are drawn one data point at a time over centuries. The vertical is one of those maps, and whether we ever finish drawing it depends not on what we can do, but on what we decide is worth doing. For now, the ceiling remains, the groove remains. The 67,000 miles per hour remains, pulling us sideways through space along a path that was set before the first humans walked upright, before the first fish crawled onto land, before the first single-celled organism split into two. The motion is older than life. It will outlast life. And every second of your existence, every breath, every heartbeat, every thought you have ever had happens inside that motion, falling sideways, forever, locked into a trajectory you cannot escape without burning more fuel than you will ever have. The solar system is not infinite. Space is not freedom. The ecliptic is not a suggestion, it is a cage. A beautiful, ancient, mathematically perfect cage built from angular momentum and gravity and the conservation laws that govern every object in the universe, and we live inside it, moving at 67,000 miles per hour in a direction we will never feel, trapped in the groove, staring at the ceiling, wondering what is up there and whether we will ever find out. You are moving at 67,000 miles per hour right now. You have been moving at that speed your entire life. You will be moving at that speed when you die. And in all that time, across every second of human history, we have barely glanced in any direction except the one we were already facing, sideways, along the groove, following the path carved out 4.5 billion years ago when a cloud of gas collapsed and started spinning, and everything that came after inherited that spin. The ecliptic is not just where we orbit, it is where we look, where we explore, where we aim every telescope and launch every spacecraft, because staying in the plane is cheap and leaving it is not. We have convinced ourselves that the flat band where the planets live is the solar system, that the groove is the map, that everything outside it is empty space, interstellar void, nothing worth the cost of reaching. We were wrong. The sphere is larger than the disk by a factor so enormous that the disk becomes a rounding error. The Oort Cloud wraps around us in every direction. Rogue planets drift through the vertical by the billions. Interstellar objects pass above and below the plane constantly, invisible, untracked, carrying information about the galaxy we will never collect because we are not looking up. The solar system we think we know is a thin slice through a structure we have barely begun to map. And the reason we have not mapped it is not physics, it is choice. We chose the groove because the groove was easier. We are still choosing it. Every mission we fund to Mars, every probe we send along the ecliptic, every survey we run looking at the same narrow band of sky is another vote to stay in the plane, to keep moving sideways, to ignore the ceiling. The vertical is not waiting for us. It does not care whether we explore it. The rogue planets will keep drifting. The Oort Cloud will keep shedding comets. The blind spot will stay blind until something falls through it that we cannot ignore. And by then, the knowledge we needed to understand what was happening will still be decades away, locked behind missions